and has more than 35 years of rich experience in teaching, research, and consultancy. With strong foundations in mathematics and statistics, he pioneered several new concepts such as interdependent communication network models with dynamic bandwidth allocation, new symmetric distribution, family of bimodal distributions, generalized Laplace distribution, generalized logic distribution, to name a few. Sir has got Distinguished Statistician Award by ISPS, Fellow of AP Academy of Sciences, Fellow of ORSI. Dr. Srinivas Professor Rao guided 54 students for PhD degrees in statistics, mathematics, computer science, mechanical engineering, and electronics communication engineering. He is one of the most versatile professors Andhra University has. He published nearly more than 223 research papers in national and international journals of high repute. He successfully completed 12 research projects funded by Government of Andhra Pradesh, UGC, DSP, Ministry of Family Welfare, and conducted more than 28 international conferences, seminars, and training programs. Hello? Hello?
Yes, madam.
Yeah.
Okay. Sorry, I'm getting some cross connection. Okay, I'm hearing. Okay, fine. It is clear with you people, no? On the other side?
Yes, madam.
Yes.
Okay. And another feather in Sir's cap is he is one of the certified auditors for us. And under his guidance only IQAC has nurtured itself. And sir, with your permission, I would like to admit that under your guidance, IQAC now, whatever it is in its shape, and yesterday only Outlook ranks have been released, sir. And Andhra University secured 16th position in top 75 universities in India ranking in India. And Andhra University is 5th in the top 70 public state universities in India, sir. And these are the rankings given by Outlook for the year 2020. In the same way, in NIRF, we stand in 16th position. And India Today also has rated Andhra University as 12th among the universities. And Sir has served as a lead consultant for TCS Bangalore, Satyam Engineering Services Hyderabad, ADB Solutions Hyderabad, Bharat Heavy Electricals Limited Hyderabad, Aurobindo Pharma Hyderabad, Dr. Reddy's Laboratories Hyderabad, Sagar Cements, Visakhapatnam Port Trust, and Lucas TVS Chennai, and several other corporate companies. Sir is elected President of Indian Society for Probability and Statistics and Regional Coordinator of AP Academy of Sciences, Visakhapatnam. He was elected Vice President, which is a very honorable post, for Operations Research Society of India during the periods 2011-14, and elected Chief Editor of JISPS, published by Springer during 2010 to 2018, and Associate Editor for Operation OP Search, published by Springer during 2014 to 2018. He also served as Vice President Operations of JBS, an MNC company, during 2004 to 6 on lean from Andhra University. And Sir has also wrote a book on model-based color image segmentation. Sir has patents also to his credit. Sir has 3 patents filed. And Sir, with this brief biodata of yours, I welcome you once again to this session. And dear participants, really it is a privilege here to have Sir among us. And Sir's session will be from 3 to 4:20 as he has a meeting. Sir, once again, thank you on behalf of Andhra University and JNTU Kakinada, University College of Engineering Vijayanagaram, for accepting our invitation, and in spite of your busy schedule, you have accepted our invitation. Thank you, sir. Over to Professor K.S. Rao.
Thank you, Lalita Bhaskar, for your nice words. And good afternoon, friends. Now we are going to discuss about the Are you able to see the screen? Hello?
Sir.
No, sir. No.
Are you able to? No?
No, sir.
No. Okay. Presenting no
Sir, at the bottom of the thing
window.
you have present.
Yeah, I am doing that.
After pressing present now, you have an option called your entire window screen, sir.
Yeah.
Then you can.
Are you able to see now?
Yes, sir. Yes, sir. Open the. Yes, sir. Yes.
Okay. So at the onset, I thank Professor Lalita Bhaskari and her team for giving me an opportunity to interact with you. Interacting particularly with the young faculty members and research scholars who are attending this faculty development program. And today's my talk, as assigned by Lalita Bhaskar, is multiple regression analysis and its allied area. So I will be talking on multiple regression analysis, assumptions of regression analysis, stepwise regression, also known as best set regression, logistic regression, and their applications. So these are the, in this, just to say 80 minutes talk, I will be covering this. Because some of you might have heard some of my lectures earlier which I delivered in different platforms regarding the regression analysis, and that there may be a little overlapping with that because the theory does not change with that. So now coming to this. Often we come across the word regression analysis. In several research studies, several areas, particularly in machine learning, data analytics, computational methodologies, we used to go for data analysis means there will be a part of regression analysis in that. So why this regression analysis is so important? Why we have to learn this? And what is this usage? Because in data analytics, why is very much used is to establish the relationship between the variables. Usually we have to consider the variables and their relationship in order to have exploratory analysis and explanatory analysis. In both the cases, we should have to establish the relationship. So unless we know the relationship between the variables, we cannot analyze further and further. So to have the relationship, what is the way? We have to go for regression analysis.
Sir, sorry to interrupt you, sir.
Yeah.
Sir, we can see your cannot see your presentation, sir. Means
Slides, sir.
Somebody told that already you got the slides?
Sir,
Yeah.
no, sir. We can see your desktop, sir. Your Meet is open, but your presentation is not open, sir.
Presentation you are not able to see. I am doing that. Okay. Anyhow, I will do back again. Now, are you able to see this? Now, are you got
Yes,
the
sir.
Yes, sir.
Yes, sir.
Yes, sir. But make it slideshow, sir. Yeah, now it's okay. Yeah.
Okay. So now we are discussing why the regression analysis. The first one is to establish the relationship between the variables. Coming to the second one, to reduce trivial many to vital few variables. This is very, very important. In many of the cases, when we see this relationship analysis, when we conduct the brainstorming session with the associates or the stakeholders, we may get several variables. For example, in a simple classroom exercise, the response variable is the marks obtained by the student. The independent variables may be several. If I go on conducting the brainstorming with the teachers, students, the principals or the administrators looking into that parents, then I will get n number of variables, independent variable, which may be influencing, saying that it will influence the number of marks obtained by the student. But one thing will come to us. Suppose there are, if I can list out, not less than 40, 50 variables I can list out, which will be influencing the number of marks obtained by the students. But when we look into that, do we consider all the 40? Is it needed also? No. Only a very few. They are very much rated. They are called vital. So we have to reduce trivial many to vital few. That is, otherwise it is useful for dimension reduction. If the dimensionality of the variable set is very large, to reduce the dimensionality, which variables are very, very important and very significant, those variables are to be included. For that, the regression analysis will be very helpful. Another important point is to understand the processes. In any phenomenon, if you understand, how we will understand? We have to go through the relationships. We have to identify which of the variables that are influencing how the process behavior. So the process behavior can be better understand, and we can get it if you perform the regression analysis. Another most important in many of the places in predictive analysis is forecasting. We have to forecast several of the variables. So to forecast what is a forecast? If you look, it is estimating the future value with a sound scientific knowledge based on the historical data. So when we consider this, regression analysis is a more sound scientific methodology which uses data to estimate the future value. So forecasting, we have to go for regression analysis. Another very important is to identify the factors affecting the response. So this is very important. Response will be there. What are the important determinants that will be influencing? How the response will be affected? How to optimize? In order to optimize the response, we have to control the input variables. So that can be done by using regression analysis. Another most important in many of the studies, analysis, and analytical applications is baseline and benchmarking. We must have a baseline to have a comparison. To have a comparison, we must have a benchmark. How to establish that benchmark and baseline? That can be done by this regression analysis. Regression analysis will provide a baseline for the process performance. On an average, what it is happening, what you will be expecting. That is, we can have a response surface methodologies. So regression analysis is the heart for response surface methodology. So for all these things, we need regression analysis. Therefore, one has to focus on this regression analysis. Now, what is a regression analysis? What we will be doing in this? This is a very interesting and important thing. So in regression analysis, what we will be doing there? We are establishing the relationship between an output variable and an input variable. Let us say the output variable is y, input variable is x, then y equals to f of x. What is this f? F is a functional relationship. So you have to establish this functional relationship. To understand the output, we have to focus on the input. To optimize the output, we have to control the input. For doing that, x is very important, which is a controllable variable, and y is the response which we are expecting and seeing that. So we have to build a relationship y equals to f of x in our regression analysis. Then when we are establishing this relation, we have to understand what is this y and what is this x. Some cases we call y is a dependent variable. Then x is an independent variable. So y versus x we are taking. Y is the output, x is the input. Y is the response, x is the variable. Y is the effect, x is the cause and effect. That's why regression analysis is called cause and effect analysis. Y is a symptom, then x is a problem. Usually for analysis in data analytics, we have two types. of excess. One is a important consideration, signals. We will be knowing the signals, controlling the signal. Another will be knowing the symptoms influencing factors, the problems that will be giving us as a symptom. So there may be a symptom or a signal we want to analyze. For that, we have to focus on independent variable. More clearly, we talk about why is the dependent variable axis of the independent variable. There might be more than one x, not only one x. There will be several axes that will be influencing y. All such axes are to be identified and analyzed. Then only the relationship will be complete and gives a meaningful value to our analysis. So to do this regression analysis, the first and foremost step is correlation analysis. We have to do the correlation analysis before doing the regression analysis. Because the variables, some may appear to be related, but may not be. So how to get whether they are related or not, how to see it. So there are several methods. The correlation is the relationship between two variables. It measures the degree and direction, how much amount of relationship and which direction it is. That is measured by this correlation. So the correlation talks about the degree. Degree in the sense it may be very high, low, moderate, no. The correlation may be no correlation, there may be a low correlation, there may be a moderate correlation, there may be a high correlation. And then coming to the direction may be positive or negative. If one variable is increasing, the other variable is also increasing. Then we say the relationship is positive. One increases the other variable, in that way influence. And if one variable is increases, the other variable is decreasing, then we say there is a negative relationship. So the relationship that can be seen by direction, either positive direction or a negative direction. Or we say the magnitude is also very important. Then how do you do this? Correlation analysis, how do you perform? One simple methodology is scatter diagram. The another methodology is Karl Pearson's computing the coefficient of correlation. Then the another methodology is Pearson's rank correlation. And there is another methodology known as correlation ratio. So these are the four methods we can explore the relationship between the variables. One is a scatter diagram. What is this? It is a simple graphical method. Plot x-axis y on a graph paper. By looking into the graph, you can see whether the relationship is a positive relation or a negative relation, or it may be very high or it may be very low. So scatter diagram gives a bird's eye view. Of course, it does not measure any value for that relationship. So it is only a graphical method. Scatter diagram is plotting on x versus y, all the points and looking into that. Sometimes when you plot, you may not get any relationship like this. Here you could see on the screen. There is no correlation, or we say zero correlation. Then how the degree of this can be taken care when we have the correlation measured by Karl Pearson's correlation coefficient, assuming that there is a linear relationship between y and x. Under that assumption only, the Karl Pearson's correlation coefficient will be measured. So if the variables move in the same direction, we already seen that is a positive direction. Move in the inverse direction, then there is a negative correlation, and we have the range of the correlation coefficient is -1 to +1. But here there is a basic assumption to do this Karl Pearson correlation coefficient is that the relationship between the two variables is linear. They are in a straight line fashion. That is very important. So it lies between -1 to +1. Accordingly, we can do the analysis. So R does not talk about any value as it is, it will turn the either high, low, moderate or no. If it is more than 70%, we say it is high. If it is between 30 to 70, we say it is moderate. Below 30, it is low. Closer to 0, it is no. So accordingly we can see, but we cannot interpret the R value. Suppose R equals to 0.8, we cannot talk anything. We can say only it is highly correlated and positively correlated. That much inference only we can say. We cannot attribute related to 80 value simply that. So what you have to do? You have to compute coefficient of determination. The square of the correlation coefficient, R square value, is known as coefficient of determination. For example, here if you see R equals to 0.8, then R square value is 0.64. That is the coefficient of determination is 0.64. There is a meaning for this coefficient of determination. That is 64% of the variation between the variables can be explained by one of the variables about the other. That is 64% of variation in Y is explained by X and 64% of variation in X is explained by Y. That is the inference we can make out of this coefficient of determination that we can have. Then the remaining 36%, 64% if you take, 36% is left out. That is due to some other variables. That relationship is maybe in X, the influence in the variable of X, not only just Y, there may be some other variables which will be influencing. So that are accounted for 36%. That is what we can analyze the correlations with respect to coefficient of determination. We can also compute the correlation coefficient using SPSS package. So SPSS package is a statistical package which will be very useful. Of course, you could also use R programming and you could have. So in the SPSS package, if you choose the correlate, bivariate, selecting the variables, you will get the required correlation analysis. Then the output of that SPSS package, because SPSS is a simple self-driven package, statistical package, which everybody can use when they are dealing with data analytics or data sciences. So here, if you see the output of this correlation analysis, you could easily find there is a value that is with respect to this 0.6963. That is the correlation coefficient. The correlation coefficient is 0.963 in this example. Here, that is the R value we call. Then, the next immediate value will talk about significant value. So it is significant. The correlation coefficient is different from 0. That can be validated by a statistical test. A statistical test at a total level of significance, it is talking about 0.001. That is what? And 7 is the number of observations we have taken, the sample size. So the output, this is how you can interpret the output.
రొట్టెలు కూర చేస్తుంది మావయ్య గారికి రొట్టెలు చేసి తర్వాత మనం చేసుకుందాం అవునా?
So somebody is.
ఒకటే ఎందుకంటే ఇవాళ గారెలు అవి ఉన్నాయి కదా అవి తింటారు. నేను వస్తానండి.
You please unmute. Madam, please unmute. So the correlation matrix, you can easily see it is a diagonal elements. All diagonal elements will be 1, and we can also get the correlation matrix when more than 2 variables are there. You could have the correlation matrix. Based on the correlation matrix, you could interpret whether the variables are dependent or independent. This is a very important consideration for going for next step of regression analysis. When we are taking this regression analysis, here correlation analysis is the most important. We have to see what is the R value and what is the significant, whether they are related or not. But the correlation analysis will talk about only degree and direction, but it does not talk about the explicit relationship between the dependent variable and the independent variable. That means, suppose if I change one unit of the dependent variable, how many units of change I can expect in the independent variable? That is more important for me as an analyst. Unless I know that I cannot apply my controls on the input variable. To apply the controls on the input variable and to optimize the response variable also, we must know how much influence of change in one variable will be there on the other variable. So to have that, the regression analysis is more important because correlation analysis cannot give that. If you change one unit of your independent variable, how many units of change you are expecting in your dependent variable? That is very much important. For that, we have a simple linear relationship. We'll talk about first a simple linear regression, multiple linear regression. Why it is called multiple? Because we are using several variables. The independent variables may be more than one. If it is only one variable, then we say it is a two variable regression or a simple regression, y and x only. But more than one, if you have x variable, here x1i, x2i have written the model. So in the model you have to relate that by a mathematical equation. The linear relationship between the dependent and independent variables is y equals to b0 plus b1 x1i plus b2 x2i plus ei. Ei is the error term. So in this, to have the regression, the first and very important is model selection. What is the most important model we have to have the predictors that explain the most variation in the response variable? That is, they have to identify the x's which will be influencing effectively the response variable. Then we have to take evaluation of the assumption. So linear regression is based on certain assumptions. We have to validate, we have to verify whether those assumptions are satisfied or not. Suppose if those assumptions are not satisfied, then we have to take the corrective action. Then only we can have a complete regression analysis. Not just by clicking a button in the computer package, you will get one value of the regression and simply taking that value and writing the equation. The very important is to have the correct model, the evaluation of the assumptions. And once the assumptions are there, then you have to validate whether the model works well or not. That validation is very important. So for any model, these three steps are important. One is the identification. Model selection is the most fundamental. Which model it is. Second one is evaluation of the assumptions and estimation of the parameters in that. Third one is validation, diagnostic check. We have to validate, we have to verify whether the model works well or not. So these are the very important considerations which we have to take care. So if you take the P variable regression model, the P variable, suppose the variables are P, independent variables. Then those P variable model you could write yi equals to beta 1 plus beta 2 into x2i, beta 3 x3i plus beta p xpi plus epsilon I. Or here P minus 1 independent variables because x2 to xp, P minus 1. And y is one variable, therefore it is called P variable regression. Y is the dependent variable, x2i, x3i, x, they are the independent variable. Then beta 1 is the intercept. Irrespective of the independent variable, there is a general effect. The general effect is measured through beta 1. Then beta 2, beta 3, beta p are called partial regression coefficients or regression coefficients. Simply we call them as regression coefficients. So these regression coefficients we'll talk about will be very useful for interpretation. So we have to analyze the regression model based on this regression coefficient. Suppose if we change x2 by 1 unit, instead of x2, I have put it as x2 plus 1. Then what happened in the y? There is an increasing of beta 2 because beta 2 is positive. So if I use 1 unit in x2, beta 2 units are changed in y. Beta 2 units are changed in y. Similarly, if I change 1 unit in xp, beta p units are changed in y. So that is the interpretation of these regression coefficients. So regression coefficients are very, very important for interpretation. Then most important component in the regression model is residual term. Many people call it as a disturbance, noise, or error. Some of the engineers may call it as a noise. Some people may call it as a residual. Some people may call it as a disturbance. Some people may call it as an error. But statisticians or data analysts call it as a random component. The residual term associated with each observation I is a random component. This random component plays a vital role in the analysis of the regression model. So you could write this n observations, set of n observations, n sets you will have. These observations can be represented in a matrix format. The matrix format here is Y matrix, X matrix, coefficient matrix beta, error or residual matrix epsilon. The Y matrix is n into one dimension. X matrix is n into p. Beta matrix is p into 1. Error matrix epsilon is n into 1. So these are the important format. Often we can write in the matrix notation. Here the assumptions if you use, what are the postulates or assumptions made for the regression analysis? That is a very important consideration. So if you see the postulate, first postulate is the expected value of the residual vector. That is the error terms on an average 0. That is the expected value of the error terms is 0. That is fundamentally the basic assumption we made with. That means the error is insignificant if you consider all sample observations. So that is what the assumption. The error is nullified if you consider the averages. Second assumption is there is no correlation between the ith and jth residual terms. The error terms are independent. There is no relationship between ith and jth residuals. The error terms are independent. That is the second assumption. Third assumption is the residuals have a constant variance. The residuals have a constant variance. That means they are from IID, independently identically distributed population. The errors are IID, independently identically distributed. Then the covariance between error and the independent variable. That is, the error is independent of the independent variable. Independent variables are fixed and they are independent of all other considerations. So the covariance between error term and the independent term is 0. That is the fourth assumption. Then fifth assumption is the rank of the data matrix X is P, that is the number of columns. The P is less than the number of observations. the number of variables must be less than number of observations in order to perform the regression analysis. So, there is no multicollinearity problem. So, if these 5 assumptions hold, then the ordinary least square estimators are unbiased linear estimators. Because usually we consider least square method of estimation for estimating the unknown parameters. What are the parameters here? We have beta 1, beta 2, beta 3, so on, beta p. These are the unknown parameters. These parameters are estimated with the available data. To estimate the available data, we use a methodology. What methodology we use? Ordinary least square methodology. So the ordinary least square methodology will give unbiased linear estimators. Also, these are minimum variance estimators. These are minimum variance estimators. And these linear unbiased estimators, if they are there, what is the advantage? What we can take? Because one important is they are linear, they are unbiased, they have a minimum variance in the class of all linear estimators, so that they have a minimum variance property. They are the best linear unbiased. So as a result of it, your estimates of beta 1, beta 2, beta 3, beta p, they are accurately estimated. And they are the true values of that, so that your model is robust and you could analyze more effectively. How these OLS estimators will be done? In matrix notation, we can write y equals to xb plus e is the error term. We want to minimize the error sum of squares such that we can get the estimates. So the error sum of squares here is e prime e, that is y minus xb prime into y minus xb. So solving these normal equations, you will get the estimate. The estimator here b equals to x dash x whole inverse x dash y. This is a very important for estimating the parameters. So you are able to estimate the unknown parameters in the regression coefficients. Unknown parameters of the regression coefficients. When we are having this multiple regression, I will come to you that the validation of the assumptions. I told that there are 5 assumptions we are making. Based on that 5 assumptions only, the ordinary least square method of estimators are more effective and efficient, and we can go. If any of one of them does not satisfy, it may not come. Very shortly I will come. Before that, let me tell you how the regression analysis is performed. The regression analysis, when we are doing it, we are establishing a functional relationship between y and x's. There is a multiple x values. So here, one of the important consideration is 1 unit change in the independent variable, how many units of change you are getting in your dependent variable. You are estimating beta from the sample data. Now the question is whether this beta, estimating this beta is one important part, then the estimated value, is it really significant? Why this? You have taken only a part, a sample, and building the regression equation for the whole universe, whole phenomenon. But you are taking only a part, you are applying inductive logic. Since you are applying inductive logic, you are using a sampling theory. Based on a sample, you are inferring about the whole universe. Now, your beta I is estimated using your sample observations. So, you got beta I equals to 0.2. Whether this 0.2 is meaningful or not, is really true or not, it is only a sampling fluctuation. Because of the sample that you have taken, it is 0.2. Or originally, inherently, it is 0.2. That is to be tested by using statistical test. For that, we have a null hypothesis. That null hypothesis is H naught beta equals to 0. Against the alternative, beta is not equals to 0. So this can be done by t-test. According to the t-test, whether beta is 0 or not, for each and every coefficient we perform the t-test and we can do. That is the one type of test. A series of tests we'll do for every beta I. Beta 1, beta 2, beta 3, beta p. That is one part. That is very much important, whether that is a significant or not. Another very important is overall goodness of fit of the entire regression equation. You have assumed that a linear relationship between y equals to f of x. The x's are linearly related. It may be, it may not be. It's only a basic starting. So your perception may be correct, may not be correct. How do you validate? You have to perform analysis of variance with respect to the regression. That will provide the goodness of fit. For that, you have to do analysis of variance. To do that, there comes the skill of the data analyst. How good he is. For doing this, fortunately, we have a package, SPSS or Minitab or any statistical package. Or you could write in our programming also. Now, so the output will be looks like this. What is the output here? First, you will get a correlation matrix. You will get a descriptive statistics. Looking into the descriptive statistics, we have a correlation matrix. Taking this correlation matrix, we see whether the independent variables are really independent or not. If they are not independent, there is a multiple. So first we have to see whether they are independent or not. Because the independent variables are independent, then your analysis is correct. So you have to make an interpretation with the correlation matrix first. Suppose if the correlation matrix talk about, they are fine, they are independent. That the small correlations that appear may not be highly significant. Then another important thing comes as a model summary. Look into this model summary. You have R square, adjusted R square. So look into the R square and adjusted R square. R is the multiple correlation coefficient. So R square talk about the percentage of variation in Y with respect to all the independent variables. But because you have taken a sample and you have estimated the parameters, you have to make an adjustment to that R square. Because some of the parameters are estimated while computing the R square value. So the adjusted R square will be talking about. And this is interpretable. You have to make an interpretation with respect to this adjusted R square. So when you are taking this adjusted R square value, it is 0.805. To make an interpretation, you have to come to F. There is a F test that was done. So the F test you have to see, it is 0.000. That means the adjusted R square value is significant. How do you say significant? The F test, ANOVA is doing a F test. In that F test, the level of significance at the given level of significance, the critical value you have to look. So the probability p value computed for the critical is 0.000, less than 0.05. What is the 0? 5. 0.05 means it is a 5%. This 5% error is type 1 error. You are tolerating 5% of tolerable error, that is type 1 error. So if this value is less than 0.000, then this R square value is significant. So we make an interpretation now. R square is 0.805. This is the linear relationship is valid, and because F is less than 0.05 and the adjusted R square is meaningful now to make a interpretation. So the interpretation if I do, 0.805, what is the interpretation I can give? I can give that converted into the percentage. 80.5% of variation in Y is due to all these X independent variables. 80.5% variation in Y is due to all X's jointly. Jointly they are influencing. Then I can come and see the important table. The table that was here, beta coefficients. Now I have to see the beta coefficients. In this beta coefficients, if I see the beta coefficient constant, that is the intercept is significant because it is also 0.05. So now I can use beta naught. Then here it may be the efficiency, mileage. The response variable Y we are taking as mileage. Mileage is influenced by vehicle weight. Vehicle weight is also significant. Then comes time to accelerate. Time to accelerate is the third one. If you see the third one, it is 0.479. That means it is more than 0.05. Therefore, this, if I call this as beta 1, this is beta 2, this is beta 3. This beta 3 is not significant. Since beta 3 is not significant, I cannot use it in the model. Similarly, other parameters I used. So beta 3 is, even though this value appears to be 0.072, but 0.072 is not meaningful because its significant value is 0.479, which is higher than 0.05. Therefore, I cannot use beta 3 is equal to 0.072. Hence, what I have to do? I have to drop out this variable. I have to do further analysis. Why this happened? Why this variable? I consider this variable time to accelerate is also very important for the mileage. But it says that it is not very important. Maybe it has correlated with other variables. So, a correlated variable is used. So, the correlation matrix I have considered here, I have to look into. If I look at the correlation matrix, I can easily see what is its significant values. That part we can get. So, the very important next step in this part is nothing but of looking into which coefficients are very, very significant. This problem happened because of multicollinearity. That is one of the assumptions that the independent, two or more independent variables in the regression model are highly correlated. If they are highly correlated, that is easily seen in that. So, what is that? If they are correlated, I cannot use both the variables. If I use both the variables, my model will be wrong. I am doing wrongly. So, what we have to do? We have to identify whether there is a multicollinearity is there or not. This multicollinearity problem, maybe there are some of the independent variables appears to be correlated. So there may be a perfect collinearity, there might be even a moderate collinearity, the multicollinearity problem will be there. So we cannot use the independent variables and that regression analysis as it is because there is a multicollinearity problem. If multicollinearity is there, high R square value, but F test may not be significant. Fortunately, in that, F test is significant, but in many cases, high R square value, F test is very insignificant. Or few or no statistically significant t tests, t values, beta coefficients. Parameter estimates drastically change values because statistically significant when excluded some of the independent variables from the regression. Because there is an interaction effect that plays a vital role, therefore, the correlation of one variable with the other is influencing. I cannot use that independent consideration. How can I do that? I may see the correlation matrix, or I can use variance inflation factor. So correlation matrix already I have shown you. But this correlation matrix, it is very difficult to interpret and take care. Even though we do, sometimes there is a small correlation that may be there that may influence. So very important consideration for us is the variance inflation factor, VIF. This is the most effective, efficient methodology to identify multicollinearity and also useful for removing the multicollinearity. Variance inflection factor measures the relationship of all variables simultaneously that they avoid two at a time. Disadvantage of correlation matrix. VIF is based on regression of each variable on the remaining variables. This is very important. Variance inflation factor, what you will be doing? One independent variable you take all the remaining independent variables. Now run the regression, assuming that particular independent variable as a dependent variable. That will provide the variance inflation factor. So, in this, variance inflation factor is to be calculated as, suppose Rj square is the multiple regression coefficient we obtain, assuming that this independent, one independent, jth variable as the independent, dependent variable, remaining all as independent variables, and run the regression. Then I will get Rj square. Then I can use VIFJ is 1 by 1 minus Rj square. And this value I will calculate for all j's of the independent variables. Using all this, if VFI are 1, then there is no multicollinearity. Greater than 1, there is some degree of multicollinearity. Of course, most of the cases, it is highly difficult to eliminate the multicollinearity problem completely. Because out there you may take some of the variables may be little related. If they are very little related, we may not bother. They are not that much bad. That insignificant correlations can be ignored. How do you say that is an insignificant correlation? If VIF is less than 8 or 10, usually 10 is a bigger value, some people consider as 8. VIF are considered to be bad if they exceed more than 10. They are very bad, we cannot use it. If they are less than 10, we may consider they are. So we calculate all VIFs, identify for which VIF is large. That variable is to be dropped out. So the variance inflection factor, if you say 3.58, we may consider there is no serious collinearity. If there is no serious collinearity, we may consider that variable. If there is a serious collinearity, we cannot. Suppose in the example, ankle diameter, waist grit, forearm grit, and height, if we choose, chest grit and shoulder grit and waist grit and bicep grit, all upper body measurements, they may be more strongly correlated rather than the lower body parameters. So you have to choose which type of relationship they have. So here the variance inflation factor, one of the variance inflation factor, if you see, it is 12.4729. You cannot use this variable. First, immediately you have to drop out this variable so that the multicollinearity problem can be eliminated. So the multicollinearity problem can be solved by dropping which variable is there. So to check the collinearity measure, this is the way we can take. We look into the drop that variable, go by step consideration. If you use this step-by-step consideration, you could have the required. How do you do that? Here you have a backward selection, a simple methodology. Put all the variables first. Calculate all possible independent variables on the dependent variable. Run the regression. see that full model. If the full model f is not significant, then we cannot analyze, we cannot interpret the R square and other values. We cannot interpret the p values. So what we have to do? We have to drop out. How do you do that? Go by backward selection. This is also known as stepwise regression analysis. That is, I will give the best subset regression. Stepwise regression or best subset regression. In the best subset regression, regression model using the maximum R, which maximizes the R square value. That is to be taken care. For which R square value is more, that will be the taken care. So we have two methodologies to select. It may be the forward or it may be the backward. Backward in the sense, put all the complete model, eliminate one after another, you will get all the models. With the combination of those models, you could get. So stepwise regression, you will be using either a forward regression, adding the variables, backward regression, removing the variables. So in the given total set of independent variables. So this will provide the stepwise regression analysis. In the stepwise regression, SPSS package or several of the statistical packages provide directly in the stepwise regression. So in the stepwise, the advantage is we can also reduce trivial mean to vital few. Why we can do? Whichever R square maximizes, that model is the best. Sometimes unrelated or redundant variables, if we include, the R square value will be drastically affected. So by eliminating that redundant variables, you could improve the R square. You could optimize the R square value. Not only just doing the multicollinearity problem solving, the stepwise regression will be helpful for us to take care about reducing dimension reduction. That is reducing trivial many to vital few. That can be done here. So two methodologies we can adopt, either put all the full model, then come to the actual models, or we may go two variables we consider, going on adding the variables, we have the complete. So this type of regression we can do, and SPSS provide the facilitate this type of regression line. Then another important assumption, heteroscedasticity we call. Heteroscedasticity is we have a model like that. And the error terms has the same variance, constant variance, sigma square. That is the one important assumption we have taken there, IID, independently, identically distributed. So the error, the residuals, the random component is having a variance of sigma square. But many cases, it may not be so. If it is constant, it is fine. But in some cases, the errors are not homoscedastic. Homoscedastic means they have a constant variance, which is the assumption we made for doing the regression analysis. But unfortunately, in some cases, the variances may not be constant. If they are not constant, then what will happen? The flatted, the curve will be, some cases it will be very peak, some cases it will be very much flatted, so that the regression will be more heteroscedastic. The observations will be more dispersed. The error term will be. So we cannot use it. As a result of it, what will happen? The ordinary least squares are not unbiased and inconsistent. The standard errors will be very high and biased. F statistic also may be very erratic. So we cannot use the T and F statistics if there is a heteroscedasticity. How to identify the heteroscedasticity? The heteroscedasticity can be easily done by seeing the OLS, residuals. So you could estimate that, testing the presence of heteroscedasticity. There is a test. White has given this by name a statistician, a data analyst, who is White, developed a test. Two test procedures were given. Here what he is telling, consider the general linear model, first model, where UI is the error or limited model, in which you have error variance is homoscedastic, the variance is sigma square. Now the null hypothesis is variance is sigma square into some function of x. It is a some function of x. Now write the error term, error square as another regression with respect to the independent variables, where Vi is another residual. Here the null hypothesis delta 1 equals to 0, delta 2 equals to 0, delta k equals to 0. If deltas are 0, then there is no heteroscedasticity. They are homoscedastic. So the observation of Ui is not known directly. So what we will do? We will run the regression, we will predict the values of y, then observed value of yi is there, estimated value of yi hat is there through regression, yi minus yi hat will give you ui, the residual value. Ui equals to yi minus yi hat, ui square. So with this ui square, now you could run the regression and you will get beta 1, beta 2, beta 3, these values. Once you will get these values, here you could calculate the regression value and you will have a f statistic given like this with this statistic. The f statistic is f equals to r square k by this. Then if this follows a f distribution, use that. See whether f is very large, that is calculated value is bigger than the critical value. We reject the null hypothesis. What is the null hypothesis here? They are homoscedastic. Therefore, there is a heteroscedasticity present. Otherwise, you can do another test also. Here in this test also similar. You will construct ui square, run the regression, use the f, but here you are adding some more the interaction effects also. So using the interaction cross product terms, you may be taking more effectively if your number of variables are more. So this will be providing heteroscedasticity. Once you have corrected how to correct it, you have identified, no doubt, heteroscedastic. Then how to correct it? The correction can be done if you know that h value. If h is known, then each variable can be divided by root hi. Variance is sigma square hi, so standard deviation is sigma hi, root h. So with each and every value divided by root hi, run the regression. But unfortunately, these h's are not known to us in the directly from the data set or observed estimated value. So what we have to do? We have to estimate that hi value. How do you estimate that hi value? You could estimate by using this. Ui is the estimated value. Take log of ui hat and run a regression like this. Run a regression, gi hat equals to log of ui hat equals to this. Here you could estimate alpha naught, delta 1, delta 2 hat, delta k hat. All these are estimated. Now you could write hi hat equals to exponential of gi hat. Exponential of gi hat. So using this hi hat, now transform the variables. Each observation is divided by root of hi of the corresponding hi hat what you have estimated. So this will transform and eliminate the heteroscedasticity of the error term. As a result of it, you will get the required corrected values. So this is how we have to eliminate heteroscedasticity. The another very important assumption is autocorrelation. What is this autocorrelation? The error terms are correlated. So there is no correlation between the disturbance terms, the error terms. That is the another very important assumption. So the linear regression model we are taking expectation of this. Here as a result of it, the OLS are no time they are blue and all your F and T misbehave. They are not consistent, the estimator. So you will get autocorrelation. How do you estimate this? You will have UT is rho into UT minus 1 plus error. Therefore, the reason for this is incorrect functional form, non-linear model. Instead of that, we are using a linear model, or some of the explanatory variables or dependent variables may not be correlated, and some of the things is that in many of the observations, particularly if you take the time series data, you have taken that. Therefore, what is the very important consideration? Here, you will get false inferences and the variance estimates will be underestimated and large T statistics will come and no insignificant F value. So how to do that? It can be done by several methods. One of the simplest method is graphical method, but not very clear. But the third one, Durbin-Watson statistic. This is very, very important. Not only just plotting that, the Durbin-Watson statistic will talk about this. It is a wonderful methodology. Here the ratio of sum of squared differences in successive residuals to the residual sum of squares measures only presence of first order autocorrelation and it assumes that lag of dependent variables is not included. D as that is measured as D, unique critical value. So we have upper bound and lower bound for this. How you will be getting that? D is approximately equals to 2 into 1 minus rho, or D equals to 0 if rho equals to 1. Similarly, you will get all the values. So you could have rejected the null hypothesis, there is no autocorrelation if D is less than DL. Accept the null hypothesis if D is greater than DA. DL is the D value, lower bound of the D, DU is the upper bound of the D. If we are say inconclusive, D lies between these two. Then we have to add some more sample points because sample is inconsistent. This can be done by this. Also, box-Lenging test, autocorrelation fourth order. So gamma k you will calculate. Gamma k is that, rho k is gamma k base, that is the covariance. Covariance by variance you will get, and rho k follows, and 0 1 by n. By this, you could also do this. So box and Lenging Q test is available in that. So Durbin-Watson statistic will be helpful as well as box and Lenging test. So this can be applied and we can have that rho k square by n minus k follows a chi-square distribution with m degrees of freedom. So we can test. Or we can use Durbin-Watson statistic decision rule. If I use the Durbin-Watson statistic decision rule, I can have 0 to DL. If the D value lies we have, no decision in this, DL to DU. No autocorrelation if it lies DU to 4 minus DU. No decision again here. Here it is autocorrelation. It is a positive autocorrelation. It is clearly a positive autocorrelation. It is no autocorrelation. In this case and in this case, there is no decision. So in these two cases, what you have to do? You have to increase your sample size to study that because there is a autocorrelation problem, but you cannot take into this. The data is insufficient. So you have to add some more observations to have an appropriate value. Suppose once this autocorrelation is present, then how to correct it? The correction can be done in this. Detecting, we can use DW statistic. Suppose if you have the explanatory variable, there is a table given, upper bound and lower bound for the sample size, given sample sizes. It was given using that. Any statistical monographs or statistical tables will have the tables of DL and DU. This Vita has given these tables very clearly. And in this case, here D is calculated 1.61 and N is 60. N is 60, 1.61. So you have 1.35, 1.48. Accept the null hypothesis because it lies between these two. Therefore, you could have. This can also be done by your statistical packages. Statistical packages, you will get Durbin statistic. So this clearly shows it is a first order autocorrelation problem. There is a autocorrelation. So this can also be done by your run test. That is time diagram. By plotting the points, you will get the residual versus. Or partial autocorrelation and autocorrelation will also tell whether they are autocorrelated or not. So correcting it, we can use this model. Suppose you have this model, write another model, epsilon t equals to rho into epsilon t minus 1 plus mu t. Now change the model in this way. Change this model. Here you have to take these error terms. Epsilon t is estimated with your previous observations. So once you have that, you could have this model, rho into epsilon t minus 1. Now you could write in this, take yt minus rho of yt minus 1 equals to this value. Rho is the first order autocorrelation. So this autocorrelation, this model you could now use. Using this model, you could have a generalized model in this way by taking this short. Now you could estimate beta naught hat, beta 1 hat and these values. So these are the correct the generalized model. Autocorrelation coefficient will be taken out. So usually by using the Cochran-Arquette method, that eliminates the problem of serial correlation. In this Arquette method, we can use directly by adjusting the values. Once the values are adjusted, now you could see the Durbin statistic is 2.20. Earlier, same problem, you will have 2.20. So that's how you could modify the model itself and get the required value. And another basic assumption we are using. Of course, for wireless estimator, there is no problem of normality. But most of the cases, the analysis, the testing, the F-test and T-test we are using. For using the T-test and F-test, we are assuming that the error terms are normally distributed. Why they are normally distributed? Do they be normally distributed? No. Maybe. But because of the central limit theorem, assuming that the sample size is very large and the population is having a certain moderately rational conditions, that was satisfied. But many of the cases, it may not satisfy the central limit theorem. Then the Gaussian assumption may not be true. How to validate whether it is a normal or not? There are nearly 10 tests available to test the normal. Among all, we can take the probability plotting, PP plot. So probability plotting we can have, and we can see our Kolmogorov-Sihorst test we can use. One of the tests we can see, if it is Gaussian, we are very happy and we can analyze and we can take the interpretations of that. Gaussian is like this bell shape. Or in a PP plot, all points lie on the straight line. Then we say it is Gaussian. If all points in the PP plot lie on the same line, straight line, then it is a probability plotting. We say it is Gaussian. But some of the cases, it may not be. If it is not, then what to do? If it is a non-normal, the error terms are non-normal. How to do it? Then you have to convert the data. You have to use transformation. What type of transformations you could use? You may take y square. You may take y cube. You may take root y. You may take 1 by y. You may take 1 by root y. Or you may take log y. So, or log to the base e. Use this transformed data, run the regression. Then you will have, to some extent, you can resolve that. But it is not exactly correct. The transformed variables, again interpreting with the transformed variables may be very, very difficult. The meaning of y may not be having the meaning of y square. Then again converting y square and talking about in terms of beta, you cannot simply take root of beta I. The regression coefficient may not be root beta I. Y square, you got estimated beta I for y square value, that for y, the beta, root beta I is not the regression coefficient. It's cherry. So, it may not convey the same inferences what you will be getting. Therefore, you have to identify using the Pearsonian system and doing that. But it is also not very important in that. So this is what you have to do the regression. When you are doing the regression, you have to be very careful with respect to the part of the variables that you have taken and their assumptions and making the correct interpretation with respect to the multiple regression as well as the subset or the best set regression you are taking. Now we are going to a very interesting part. In some of the cases, so far we have taken y and x as both are quantitative variables. They are quantitative, they are measurable directly. But in some cases, the dependent variable may be discrete outcome. Then categorical, profit and loss, pass and fail. So we may not have this. Similarly, satisfaction level, satisfied or not satisfied, more satisfied. So like that, we cannot give direct measurement to them. A categorical variables may be there. When there are categorical variables, you cannot use the multiple regression analysis directly. In such cases, what you have to do? Simply saying that I cannot have a categorical data in the dependent variable, I cannot analyze is not the correct. So what we have to do? We have to take logistic regression. So logistic regression is a commonly used technique when your dependent variable is categorical. Two discrete outcomes, two or more even. There may be a Poisson logistic regression, there may be binomial logistic regression. The logistic regression, the outcome variable is categorical, and the purpose of analysis is to assess the effect of multiple explanatory independent variables. They may be, the independent variables may be numeric, may be categorical. It does not matter. So in both the cases, we can run these. Here, the categorical values of the dependent variable, we can write 1, 0, binary. Simple case I am considering. Of course, in Poisson, you may take 0, 1, 2, 3, 4. Like that. But binary case I am considering. In the binary case, you have to write 1 for success, 0 for failure, 1 for probability, 0 for loss, like that. A way of estimating the probability P in the dependent variable, way to link dependent variables with respect to the others, and doing the test. That is what. So the criteria variable, dependent variable may be categorical and continuous, what we are talking about. Here, odds of success. P is the probability of occurring an event. Occurring an event means occurrence of the success. If the occurrence of the success is taken as an event, the odds of success is P by 1 minus P. Okay? 1 minus P is failure. P is the probability of success, 1 minus P is the failure. Then odds of success is P by 1 minus P. So here we have to take the odds equals to e power, the model, explanatory model we are writing, e power alpha plus beta 1 x1, beta 2 x2, beta p xp. x1, x2, xp are independent variables we have. So when these are the independent variables, you could write how to estimate beta 1, beta 2, beta 3, beta p. So these can be estimated by taking log of p by 1 minus p is equals to log of this, because E is the common logarithm base. Then logit P equals to alpha plus beta 1 x1, beta 2 x2 plus beta p xp. The coefficient beta 1, beta p are such that sum of the squared distances from the observed and the predicted value. In the regression line, when we have taken this, these here beta 1, beta 2, beta p are not similar to the values that you have explained earlier. Multiple regression is different, logistic regression is different. Don't get confused. Both are not same. They are the different concepts, different ideas, but both will be talking about the relationship among the variables. They are establishing the relationship among the variables. They are analyzing the relationship among the variables. In logistic regression, what we are doing? The dependent variable is a categorical variable. Whereas multiple regression, what we are considering? The dependent variable is a quantitative variable. It is measurable directly. Here it is not measurable directly. It is a categorical variable. So we have to take in this. Once we are taken, simple consideration. Let us consider the logistic regression as an example. A particular farm, agricultural farm or something, a farm is there. Then we have two independent variables. One is the size of the farm, the other is age of the farm. Or in any organization, a banking or any business organization. And what is a dependent variable? It's a performance variable. The performance is dependent on the size, that is number of size in the sense, number of workers in the organization, number of employees is called size of the organization, is how long it has been. So depending on these two, the performance of the organization. Performance we can consider here. Size is measured as number of employees in hundreds working in a firm. Age is the number of years. So here 0 indicates the profit, 0 indicates the loss, 1 indicates the profit. So loss and profit, these are the very important. A sample of 50 firms are selected. And we want to analyze. What we want to analyze? Performance of a firm is positively related to its size or not. performance of the firm is positively related to its age or not? Is there any interaction between the size and the age? This we want to study. In that, do they have an influence? Performance is influenced by these or not? That we want to study. So we formulate a null hypothesis. Performance is not related to the size of the firm. That is our null hypothesis. Second null hypothesis is performance is not related to the age of the firm. Third null hypothesis is size of the firm interact with its age in determining the firm performance, such that effect of size and performance increases with the age of the firm. Bigger and older firms have better performance than bigger and newer firms. So logistic regression we can calculate. We have calculated 50 observations. We have taken. There are two models we will get. One is with interaction. The other is without interaction. So we have two models. Every logistic regression, we can build two models. One is without interaction. The other is with interaction. So in that, if I run SPSS package, will do that. So here the variables, you take the dependent variable is the performance, then independent variables you will take and you will enter them, and it is a simple, you could directly go for the binary logistic in the SPSS package. If you use the SPSS package, here you will get the interaction, second model. If you enter the second model, you will get this. You will get for the first one a descriptive statistics. The descriptive statistics says how many observations are there. In that, no observation is missing. If there is any missing observation, that will be given. Then you can edit or you can delete that value. So that's what you could have. Then you could have this method 1. In the method 1, you have taken only 2. That is the size as well as this. Now you could have this. 2 log likelihood is the value that will be coming up. Here if you see the Cox and Snell and the Negnecker R-square values give an approximate value of that. In this experimentation, if you see that 0.697, that means 0.522. That is both the two things. What are those? Size and age. They influence the performance variance. It may be 52.5%, 52.2% to 69.7%. It may be in between. The variable will be in between these two values. You have to convert in terms of percentage. And the model is significant because all are 0. Here model significance. Model is significant and it lies in these values. Once you got it, now you could have how many firms it has correctly estimated. Here you could see 83.3% of the loss-making firms are correctly identified. 80.8% of the profit-making firms are correctly identified. Overall, 82% of the firms are correctly identified. This is what we can have. Then the beta coefficients. Here two parameters. You have beta 1 and beta 2. Those two coefficients are this. These two coefficients, if you see, they are also significant because they are less than 0.05. So their exponential value is directly given. And beta naught is given to be this value. Beta naught is also significant. So beta naught, beta 1, beta 2. So you could substitute these values and you could write the model. Log of P, you could write. Beta coefficients, you will be getting this and size. So positive beta coefficient for size and age means that increase in size and age of the firm, its chance of having a probability performance. Because it is beta value e power, you have to look 1.225. 1.225, what it talk about? Exponential of beta take a value more than 1. Beta coefficient is positive. It increases, then profit is also increasing. If you increase the size, profit is also increasing. Similarly, 1.16, if I take, that is also says age is increased, 1 unit, profit is also increased. If they are less than 1, these are less than 1, then there is a negative. If they are negative means there is a negative impact. They may not make. That is 1.16 for age indicate that for any 1 year increase in the age of the odds of a firm, having a profitability performance increased by a factor of 1. So this is the interpretation we can make. Also, I have another problem. Whether age and size, the collective put together, do they have any influence? Is not significant. Why it is not significant? I can easily see here. Age and that. This is 0.340. This is greater than 0.05. Since this is greater than 0.05, this is not significant. Since this is not significant, age and the size are no way correlated. Age and size are no way correlated. So the incremental change of 9.997 and not significant with respect to the p-value clearly talk about there is no need of going for a second model. So first model itself is sufficient for me. This is what logistic regression we have to take. So regression is more useful. It can be applied in several ways, particularly in business analytics, market segmentation. Regression analysis is very much useful in several, in every area of engineering, that is the response surface, in designs of experiments, at every design, pharmaceutical industries, chemical industries, everywhere. This regression analysis is the backbone for response surface and optimal input determination. So it has several applications in various areas we can see. With this, I thank every one of you for your patience listening, as well as I thank Lalita and Josna and others in her team for giving me an opportunity to interact with you.
Sir, thank you, sir.
Thank you.
Sir, K. Srinivasrao Garu, thank you, sir. I am the another organizer from JNTU Kakinada, Professor Jaisuma.
Jai
thank
Suma.
you.
Sorry, I thought Josna, I thought.
This is Jaisuma, sir. Thank you very much for your session, sir. Thank you.
Thank you. I thank every one of you. Thank you.
All the participants, you will have 10 minutes break from at 4:40. You please log in. So you will be having another session from IIT Kharagpur. Debasis Samantha will be taking the another session at 4:40. So I request all of you to please take 10 minutes break and log in again.
Sir, I have one doubt, sir. Sir, namaste.
Yeah, quickly. I have to go quickly. You could ask or you could give an email. I will respond. Or quickly you can ask. I will tell you. Hello?
Hello, sir.
Yeah.
Sir, I have one doubt, sir.
Please ask.
Tell me, what is the
Sir,
doubt?
I am working with air pollution analysis, sir. I have calculated variance inflection factors for SO2 and NO2, sir.
Okay.
In that for SO2 it is 6, but for NO2 it is 680, sir.
How much?
680.
So definitely that variable you have to drop out first and look with the other variable.
But
So
actually,
they are highly correlated. They are correlated.
but
If it is more than 10,
yes, sir.
variance inflection factor, that variable you have to first focus and delete that. Search for other variables which may be influencing that.
Is there any method to adjust beta values, sir?
Huh?
Is there any method to adjust beta values, sir?
Adjustments in the sense, what you mean by that? Estimating, I told you how to estimate beta value. There is no adjustments in that. Only estimating. So I already told you how to estimate by using your OLS estimator. Or if more estimator, you may use molecular method of estimation.
Okay, sir.
Okay, thank you. Thank you, every one of you. If you have any more doubts, you may contact me anytime. I am the principal in the College of Science and Technology, Andhra University. You may contact me without interacting with people. Thank you.
Thank you for for your time and valuable session. Thank you, sir. Sir, Debasis sir.
Yes, hello. I'm now ready, but I think your participants should need some gap, I think, because they
Yes,
just.
sir. 10 minutes break I have given them. Welcome you too, sir. So
Yeah.
at 4:40, we'll start again, sir.
Okay, no problem. No problem.
Okay.
Yeah, so now I should quit or I should be the. Okay, I mean.
You be in mute position, sir. Enough.
Okay, fine.
Shall we start? Uh, Welcome to 8th day of FDP program on data science and applications, session 2. Now I will introduce eminent personality, a professor from IIT Kharagpur. Professor Debasis Samanta, he is a associate professor in Department of Computer Science and Engineering, Indian Institute of Technology, Kharagpur. Professor Samanta is actively working in field of human-computer interaction. He aims to develop efficient interaction mechanism for people with special needs such as motor impaired people and people with other disabilities. And he developed multimodal interaction technique, text entry mechanism in Indian languages, which are new for their kinds of bridge the digital divide. Currently, he is working towards the development of next generation hands-free and touch-free interaction mechanism using brain-computer interface. He and his research team are in process of developing BCI HCI lab in IIT Kharagpur, a unique lab facility in India. He is an author of 3 books and more than 70 journals and 110 conference papers in international repute. He is currently an honorary member of editorial board of International Journal of Biosciences and Technology, USA, and a member of editorial board of International Journal of Communication Networks and Distributed Systems, UK. He is the recipient of Best Author of Year Award by Computer Society of India, Best Paper Award of 8th ADCOM Conference, Microsoft Valued Professional Award by Microsoft, USA, and author of best-selling books by PH of India, New Delhi. Sir, Professor
Thank you. Thank you very much.
I welcome you to this session. I think today you will be delivering on statistical learning.
Correct. Yes.
It's pleasure for us as well as for the participants to listen to your lecture. So I hand over this time to you, and you can at what time you want to continue, sir? Is it 6:15 or 6:30?
Today, okay. Actually, I have planned for 2 hours or so. So it will around around okay. Okay, I think it should not
Around
exceed 2 hours. Yeah.
Okay, 6:15. Okay, sir. Okay, sir. Welcome you, sir. Once again,
Thank you very much. Yeah.
start your session, sir.
Okay, so let me allow to present my lecture slides.
Yes, sir. You can present, sir.
Yeah. I just want to know whether you can see my video. I mean lecture slides.
Yes, sir. We are able to see it like see it, sir.
Okay. Thank you.
You are at live tomorrow.
Okay. So now let's start. Good evening to everybody. In fact, I have very little information about the participants. So I don't know whether they are all students or mix of students and faculty members.
They
Anyway,
are faculty, sir. They are faculty members, sir.
okay, they are faculty members. Then it is good. Okay, so then I believe that okay, I should not go. I mean, okay, I can assume that the basic prerequisite that is required in order to understand the statistical learning topic, because it is an advanced topic, and basically the basics of mathematics is very much required to understand. Anyway, I will present this topic in such a way that even if you forgot some concept or some things, then it will not be a problem for you to follow my delivery. So let's start about, okay, first I will start with the basic prerequisites. But before going to start my actual topic, I would like to tell about the statistical learning, why it is an important topic now. Now, you know, this is basically the emerging topic in computational, what is called intelligence, and it is called artificial intelligence. People are now solving the problem which could not possible maybe 5 years back. So now, basically, there is a tremendous development in the field of artificial intelligence. Now, you know, artificial intelligence, there are few important tools we usually use. These are basically mathematical concepts, I should say, like machine learning, deep learning, and then statistical learning. As you see, these are basically learning. So question definitely arises that, okay, learning means who learns actually. So idea here is that actually the machine, right? We have to train the machine. That is why here learning means machine should learn. Now again, question is that how machine can learn. So actually in artificial intelligence, machine learn from data. Now definitely data is therefore very important one concept that needs to be processed very meticulously so that your machine can learn efficiently. In the sense efficiently is that, okay, machine can solve after learning from the data. Whatever the information that you want to retrieve from the data, machine will be able to provide you. Now here is basically the question that comes is that different learning. Why different learning? Machine learning, why deep learning, why statistical learning? Obviously, there are certain procedures. So different learnings basically follow, obviously, they basically to meet the different objectives, and definitely the platform or the environment where the machine should learn. So here basically in case of statistical learning, other than machine learning and then deep learning, because in these topics you are learning all those concepts, I believe. But in this statistical learning, the machine, right, will learn from a population data. Now, obviously, population data is usually very large. Then it is sometimes it's not possible to learn or possible to collect such a massive data. Then what it is required is that we have to learn from the sample. A sample is basically subset of a population. Now here question here is that, okay, if we want to learn from the sample, which is basically a subset of a population, how the learning is efficient, or how the learning is acceptable to us. Now today basically we will see how from a sample we can learn, and that is basically the concept is called the statistical learning, and what are the procedure that is required to learn about this topic, that is statistical learning actually. So we should say we are going to learn about statistical learning. Statistical learning is that machine can learn from your sample data. Anyway, so before going to start statistical learning, let us have certain basic prerequisite. It is very fundamental prerequisite. I'm sure many of you or all of you have that prerequisite because you are the faculty member, and then obviously engineering faculty you can say, and then as an engineering faculty, being an engineering faculty, you should have sufficient mathematical background, and statistical learning needs a good background, particularly in the field of probability and statistics. So basic prerequisite will basically span within 15 minutes or so the basic mathematics about probability and statistics, so that I can make the discussion a little bit in the same context, so that you will be able to follow. So without just losing the continuity in our discussion, I just want to have the prerequisite. Now let us start about the topic that we are going to discuss about. So first we have to have the idea about sampling distribution, because I told you we have to learn something from the sample. And here one beauty is that without having actual data, right, it is not required the data to be collected from the ground or from the field and you process this data, but without collecting data, but knowing the behavior of the data, right? So how the behavior of the data can be understood, that basically helps you to understand about sampling distribution. So real life data may not be at your disposal, right? You can have the pattern of the data, and usually in all real life applications, the data that is involved, they follow certain standard pattern actually, okay? And those pattern can be mathematically described by the sampling distribution. So we shall clear our total understanding about the sampling distribution, and then how the sampling distribution is acceptable and is valid concept that basically can be argued by the central limit theorem. And we see that, okay, how the central limit theorem become a breakthrough on theorem, and for which the statistical inference is possible, or statistical learning is become a reality today. And usually there are many sampling distribution. However, for statistical learning, there are four important sampling distribution we usually follow. They are called normal distribution. There are two types of normal distribution called the Z distribution and T distribution. Other than this normal distribution, there is other distribution. It is called the chi-square distribution and F distribution. So today we just want to give a touch about all these four distribution, and then we'll jump to our statistical learning approaches. Okay, so this is plan basically. We will discuss about the statistical learning process. Actually, it is also called hypothesis testing, and we shall know about what are the different steps that is required to be followed in order to have the hypothesis testing for a given data or sample. And then we'll discuss, we'll elaborate our understanding rather, right, with 2 case studies. So that is related to the real life application. It's a very small one, but you will be able to follow it quickly. So this is basically my plan for today. It will take not more than maximum 2 hours. I will try to finish before that also, so that at the end of my presentation, I can take some questions from you if you have any doubt. Otherwise, if you have any doubt during the presentation, you please, feel free to ask any question at any time. Absolutely no problem. I will rather enjoy it, and then I encourage you to ask any questions anytime. Now, as I said already, is that, so basically data is an important concept, particularly now the data intensive, our world is basically data intensive. Everywhere we have to process the data. All those data usually come from different sources, from different sensors, from mobile data, from the social media and internet, from other lab and whatever it is not there. Okay. So these are the basically data. So data can be collected. Data can be collected using some survey or using some employment of certain deployment of certain sensors here and there, whatever the means are there. Anyway, the data should be collected. And then that data is basically, we can categorize the data into 2. The entire data, those are involved, they are basically called the population, which is usually very, very large. And as the population is large and it is not possible to handle or process or store, that is why people consider it is a sample, it is a subset of the population. Now, here the statistics, I want to say what do you mean by the statistics? So basically what is required is that we have to compute the statistics for the sample, actually the same for the population. So usually the statistics implies about a population or sample is basically what is the mean of the sample or what is the mean of the population, what is the variance of the population. Usually they are called some descriptive measures. So maybe measures of central tendency, measure of dispersion, whatever it is there. And in some other application, we can measure some other quartile, percentile, IQR, interquartile range, and so many things are there. And whatever be the sample statistics that we have to have, they are basically can be visualized or can be stored in a numerical file, whatever it is there. And there are many visualization techniques are there also by which we can visualize the data, and that is for basically data summarization. So the data can be summarized. Anyway, so idea here come about the statistical inference. This means that if we can help the machine to learn, so that machine can infer statistically. What is the statistical inference? It means that from the data or collection or whatever it is, so machine will be able to infer about statistics. This means that what is the population mean, what is the population variance and everything, because we are interested for all those things are there. Anyway, we can understand all these things with an example, which basically I will give while I will go for discussing in details. Now, in this context, one important concept that is required, because I told you data may be very large, even the sample also sometimes very difficult to collect, and even if you collect also, they may not be not satisfied whatever the requirement or the properties that is required to be satisfied by a sample, whatever it is there. So sometimes sample is really very costly, it's not that easy, rather we can say is a cost, is an costly affairs. So sometimes we may think about something else, that is an alternative approach to that of the sample that is possible to collect from the ground or field. Now, anyway, so whatever the idea, way you can collect the data either by means of sample from the ground or by some other means. Other means I just wanted to mention about is basically the sampling distribution, that is what. Now, they are actually sampling distribution. In order to define, there is a concept of random variable is required. Now, I know that random variable, what you mean is basically a random variable is basically probability that a value or some information can be having, and it is a probabilistic value. So here I just mention this is basically Px equals to x. This is basically the yeah, so this Yeah. So, okay. So Px equals to x. This is basically your random variable. Now I can give an example. So suppose I want to have certain statistics or some data, right, related to the different families, maybe say 100 families, and out of the 100 families, how many children in each family. Okay. So that information can be obtained probabilistically, and that is why you can say that x equals to x. What is the x here? Small x is basically how many children in a family. The number of children that is possible in a family may be 0, 1, 2, 3, up to 10, right? So Px equals to x. That means a capital X is basically number of children in a family. This is equals to x, and this probability that in your application, in your area, in your scenario, in your situation, and the probability that a family is having number of children is 0 or number of children is 1, whatever it is, it can be calculated by certain rule. That rule is basically called fx. Now this fx is basically a rule, as I said, and it is basically can be better described by a distribution function. It is sometimes also called probability mass function. And if x is in a discrete domain, then this probability distribution function can be expressed in a discrete probability distribution function. And on the other hand, if x is in a continuous domain, then it can be termed as a continuous probability distribution function. Now, for different application, for different pattern, for different varieties of the data in your different scenarios, there are a large number of distribution functions are known. They mainly categorize into two broad categories as a discrete probability distribution function and continuous probability distribution function. In these slides, I have listed few important probability distribution function both in discrete domain as well as in continuous domain. And it is one very interesting point to note is that most of the data that we have in different applications, for some unknown reason or whatever it is there, they basically follow a standard normal distribution function. They are okay. If it is a continuous domain, no issue. If it is even discrete domain, also no issue. So basically, they follow a normal distribution function. A normal distribution function typically expressed in terms of the mu and sigma, where mu is called the population mean and sigma is basically population standard deviation. And how the picture of a normal distribution look like, it is shown here in this picture, right? It looks like a bell shape. This is why this distribution function is also called the bell curve distribution or bell distribution, and it is proposed by Gaussian, so it is also alternatively called the Gaussian distribution function. Now there is a simplified form of this Gaussian distribution function, and it is called the standard normal distribution function, which is shown here. So you see the two form, the Gaussian normal Gaussian distribution and then standard normal distribution. They are basically same. Only the concept is that we need the data to be transformed. That means the random variable value will be with a transformed parameter, right? So what is the transformed parameter? In this case, the peak of the curve. This means that this is a maximum probability distribution that is possible for certain value, and this basically is the mean. So here x equals to 10 is the mean, and this is basically mu. Now, so if we just shift this curve so that this becomes the origin, then it is basically the standard normal distribution. Now, we usually follow the standard normal distribution because of the computation that is involved here. Because whenever we have to use the distribution function, we have to do a lot of contribution, and this is a one-time contribution because it's a constant. But for different values of x, that is why the random variable value, we have to calculate what is the probability of that fx, that is fx. So it needs this calculation. Now, this calculation can be made simplified by transforming a transformation function that is z. So it is here z is basically transform the x domain to z domain, and this becomes the simplified calculation, and that is why it is used. So that is why the standard normal distribution is known here. Now, what exactly I want to say here is that if your data follow a certain pattern, and from that pattern, you will be able to know what is the probabilistic value for certain, what is called the certain elements, so certain random variable value. Now, this pattern is very useful, and this pattern is sufficient to okay, have any your decision in your any process, that is where you have to make a decision that without collecting the data from the ground, we can follow the pattern of the data by means of this distribution function, and then we can have the idea, and then we can do it. Now we will see exactly how such a distribution function is helpful to have the pattern of your own. Now, so this is why the sampling distribution is basically here. A sampling distribution is nothing but is a distribution, or is a distribution that the probability of a sample will lie within a certain value, and that is why sampling distribution function is there. And in this regard, for the population statistics, we usually refer to the statistics as mean and then variance. So mean is basically denoted by mu symbol, and variance is denoted by sigma square symbol. And in order to make distinguish from the population to that of sample, so mean of a sample usually denoted as x bar, as it is mentioned here, and then variance is denoted by a square. So this is the notation we usually refer in our subsequent discussion without explicitly mentioning. So x bar implies that it is a sample mean, and capital A square implies that it is the sample variance, whereas population mu is mu, population mean is mu, and population variance is basically sigma square. Anyway, so now possibly you are able to get the idea about what exactly the sampling distribution is there. If your idea is not a bit clear, I can make it clear with a simple example. Now let us consider a very simple example. It is a very toy example so that you can understand what it does the sample distribution mean, because this is the main concept behind statistical learning. That is why we should have very good concept about sampling distribution. Now what I want to say is that let us consider the one game. The game consists of 5 identical balls. Each balls are of different weights. Let the weight is 1 unit, 2 unit, 3 unit, 4 unit, and 5 unit. Now, so these are the basically a set of data we can say. Now consider an experiment which consists of selecting 2 balls from the set in such a way that first we select one ball, then we can note down which ball, what is the weight of it, and then we return the ball to the set again, and again we can select the next ball. Therefore, we will be able to choose any 2 balls at random, and therefore we can take what is the mean of these 2 balls that we have selected. So we can see from the set of 5 balls, selecting 2 balls at a time, and what are the different possible number of, we can say, samples this here, because here each sample consists of 2 balls. Size of the sample is 2, and as there are 5 balls, selecting 2 at a time, so 5 square, it is basically 5 square. It is a 5 square number of altogether sample that can be collected. Okay, and these are the different samples that we have collected. This means we have selected 1 at the first draw, then again at the next draw 1, because we follow basically the game or event that we follow is basically dependent of the others. That is why, because the replacement is procedure. So that is why 1 is coming, and then 1 2 and all these things. So these are the different samples. The total 25 samples are listed here. Now in the next row, for each sample we store the result of their mean. So here the mean, and this is the mean of the weights, and this one. So what we can say is that from the population, if I say that 1 2 3 4 and 5, the different balls having weights like this constitute a population, then we can select the sample from it, and the number of samples that is possible, taking 2 at a time, that is sample size, in an exhaustive manner. That means all possible sample that is okay, we can consider. So there are 25 samples, and for each sample we can calculate the sample mean. Now here let us note about how this sample mean varies. Okay, now we will be able to see that there is an interesting pattern it follows, although it is a random event, right? But it should follow certain interesting pattern. So what we can do is that we will consider different samples and their the mean. And here you can note that there are few samples are repeated in occurs, or their mean is same. For example, 3.0 having the samples mean here and here, 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 here. So it occurs repeatedly. So let us see if we plot the sample mean in the x-axis and then the distribution of the number of samples which is having this sample mean, particular sample mean value. So here this slide is basically shows you, here I just plot the different sample means. As I say, they are the sample mean varying from 1.0 to 5.0. And here, this basically we can see, this is the distribution that 1.0 having 1, then 1.52, and here 3.0 having 5. These are the total number of samples that occurs having the mean. So here one important fact that you can think about, that the sample mean which has occurred maximum time is basically the mean of all the sample that occurs there also. So, we can take it in a normalized fashion as we have listed here in the normalized fashion, because the total 25 and divided by the number of occurrence by 25, it basically give you normalized, and this value lies between 0 to 1. So this actually the probability value we can say, that is the idea about it. So what I can say is that from the sample of 5 balls that we have considered, if we select one sample of size 2, the maximum probability that you will select the sample having the mean 3.0 is basically 0.2, or whatever the probability that is, because 5 by 25 is like that only. Okay, so this is the idea about, and what are the other frequencies less actually. So this is the one important what is called observation that you can notice, that sampling distribution follows certain pattern, and your chance that you will get the sample, right sample, which basically gives you the population characteristics. Now let us see what is the population characteristic that we have considered. We have noted that sample mean is 3.0. Now let us see what is the population mean that is possible. I have listed here the population mean mu, you can note it is 3, and then population variance you can calculate is 3.5. And from this sampling distribution, as we have noted it, it is also mean, right? So this is the mean, because the peak value occurs here. So this is also mean. And here also variance, if you calculate, variance means whatever the mean value that we have, and if we calculate their variance, you will be able to see that their variance is very near to 1. That is basically, there are certain rule actually. Okay, I will going to discuss about this rule about. So it is variance is 1.25. Now how this 1.25 I have calculated numerically, and then we can see. So what I wanted to say is that if your sample follow normal distribution, the way that I have given an example earlier, then the sample mean is same as the population mean. This means that most of the time, if you collect a sample at random, then you will be basically fortunate enough that you can say that, okay, this is the population mean. So knowing the sample mean, you will be able to tell about the population mean, and that is an important thing actually, right? But this needs to be proved actually. What is the basis of this one? Now this actually, this concept can be better proposed by a theorem. And here actually I just wanted to give the theorem informally. What I said here, if the sample size increases, the sample distribution approaches to normal distribution. And this is an important, very important observation. There are many experiments that you can carry out, like the experiment I have told you, and you can verify this one, and most of the cases you will see that it is following. Now in some situation, obviously there are always situation, we can say exceptional situation. In that case, the sampling distribution may follow something else. Obviously, there are different treatment, mathematical treatment, and this is basically beyond the scope of this discussion. But as I said, most of the real life application which basically satisfy this criteria, so this is not at all wrong to proceed with this observation. Now, based on this concept, there is a very famous one theorem. It is called the central limit theorem. Central limit theorem says that if a random samples, each of size n, are taken from any distribution, is basically any population with mean mu and variance sigma square, then the sample x bar will have a distribution approximately normal with mean mu, and sample variance, that means variance of the means of the sample, is sigma square by n. And definitely the sigma square by n, the sample variance, will be very close to that one as the size of the n increases. That is what I told you. For the sufficient large size of sample, this theorem is valid. Now question is that what do you mean by the sufficiently large size of the sample? So there are many empirical relation is known. So if the size of the sample is greater than or equals to 30, that means 30 or more, then we can say that the central limit theorem is applicable, and therefore we can proceed with the central limit theorem to conclude, to infer about statistics of the population. And it is the breakthrough one theorem. It is basically the turning point so far the statistical learning is concerned, and I can say the statistical learning starts from here actually. So if the sample size is large, then definitely we have a very good what is called the advantage from it, and then we can conclude many things, and that conclusion regarding the population. So we can tell anything about the population there. Now, so again, central limit theorem that can be again expressed using the probability distribution function, the standard normal distribution function. If we say like this, then we can say that z equals to x bar minus mu by sigma root over n, and this is basically the transformation function that we have used. So mu and s, where s is replaced. This is according to central limit theorem. A square equals to sigma square by n. So that is how you can replace it, and this becomes the z. So this basically called the z distribution. So far the sampling distribution is concerned. What it does that it basically gives a relation from the z value. Z value means is a random variable value, and it basically relate with the x bar. X bar means the sample mean, and it is also related with the population mean. This means that if two or more is unknown and other are known parameters, then we will be able to calculate from there also if this theorem is valid. As it is valid, it is absolutely it is like this one. So we'll see exactly the application of this concept in our next discussion. Now I was discussing about the normal distribution as a sampling distribution. There are few more other sampling distribution also. So I have mentioned listed here. One is the chi-square distribution. It is basically distribution of variance. So normal distribution or sampling distribution that I have just now completed, it is basically distribution of means. So distribution of mean of the sample. But again, similar kind of experiment that we can do, even for the same experiment, we could calculate the variance, and accordingly we can have the plotting of distribution of variance. Then it will follow another pattern. That pattern can be better described by a chi-square distribution pattern. Now, like z distribution, there is another distribution called the t distribution. Usually z distribution is applicable to a population where the variance is somehow known. In case, suppose variance is not known, taking the variance of sample, if we follow a distribution of a sample, then such a distribution is called the t distribution. So t distribution is another one, is more, okay, if the z distribution is a conservative one, so t distribution is more what is called the liberal in that sense. And there is one more distribution is also known here, the distribution of two samples, two statistics parameter. It is basically the ratio of the sample standard deviation by the population deviation. So there are many other distribution known, and then I'll quickly describe about each distribution. So this is obviously the standard normal distribution, and it basically gives the distribution of samples mean, and it is usually called the z function or z test actually. And then chi-square distribution takes this form. So chi-square value is here n-1 is basically called the degrees of freedom, where a square is samples variance and sigma square is population's variance. So here chi-square can be calculated if you know the sample variance and if you know the population variance, then chi-square value can be calculated. This is the idea about it, and it is valid up to the n-1 degrees of freedom. If degrees of freedom changes, then it also value changes. Now the t distribution function, as I said, in some situation mu is somehow can be predictable, but we have to predict it with the confidence of population variance. But in some situation, population variance is very difficult to know because you may not know the population variance. So in that case, t distribution is basically proposed, and the t distribution takes this form. It basically takes the chi-square distribution as a ratio of this one. So it, and more simplification that can be have it. So t distribution takes this form, x bar minus mu. It is basically same as z distribution if you note it, x bar minus mu divided by s by root n, Whereas in case of Z distribution, S is replaced by sigma. So this is basically the formula. That means the t value for a sample that can be calculated given that population mu and then sample variance, and n is the size of the sample. So these are the concepts that is basically required so that we can apply the statistical learning concept. It is there. And here is the F distribution. So F distribution is basically for 2 degrees of freedom of the 2 samples. If we take into account, then it can be expressed this form. So it is basically for one sample S1 square by sigma 1 square, for another sample S2 square by sigma 2 square. There are many situations where we have to take the confidence taking from the 2 populations and thereby 2 samples from each population. Then the F distribution. So F distribution is basically very much important when we have to go for analysis of variance. It is called the ANOVA. But ANOVA will not be covered in this lecture. We will only limit to T distribution, Z distribution, and chi-square distribution, which are basically related to our statistical learning. So now we are ready to learn about statistical learning, and this is the prerequisite that is required so that we can learn, we can understand the concept of statistical learning. So concept of statistical learning, as I said, needs the concept of sampling distribution, and just now we have learned about there are 3 important sampling distribution that is very much used for the statistical learning, called the Z distribution, T distribution, and then chi-square distribution. We will see exactly the application of the sampling distribution so far our statistical learning is concerned. Now let us start the concept of statistical learning strategies. I hope you are able to follow, and this is just prerequisite that I have mentioned. Now we will be able to understand about statistical learning concept shortly. Now if you have any questions, so I can take 1 or 2 questions so before jumping to our next topic.
Sir, I have one question, sir.
Sure, please.
Good morning, good evening, sir. Sir, sample mean and population mean. In the population mean, we are considering all the instances, and in the sample mean, we are considering only the sample values.
Correct.
So, is there any change in evaluating the output, sir? If we consider sample.
Yeah, that is what. Actually, what I want to see is that the statistical learning is it does not give the result 100% accurate, you know, but in some decision making, the result is near about, right?
Yes, sir. Yes, sir.
With certain percentage of error, but still we will be happy. So statistical learning always with certain error, right? So it is not 100%. If suppose population mu is 500, right? And by means of collecting sample, if you collect that data and you can calculate from the sample that population means 525 or 475, then definitely it's an error. But you have to be very happy with this result because you don't have to consider the population, because size of the population may be million or billion, right? But in case of sample may be only 40 or 50. So definitely with the confidence of 40 data, you have to have the confidence of millions data. So that is why, okay, right? So error is always there, right? But that is absolutely no problem. So it is not that, okay, sample will give you the 100% accurate result. So far the population mean conclusion is concerned. But if it always gives very close to the data, and how it can be obtained, that we are going to learn about it. Yes. So good question. Fine.
Thank you, sir. Thank you, sir.
Okay, we can take 2 more questions. You can note down your questions so that at the end we can have a detailed discussion about many other questions. So now let's start about statistical learning strategies. Now, so far the statistical learning strategies are concerned, there are 2 approaches, right? You are already learning one approach. It is basically a little bit, not so much truly or pure machine learning, but it is very close to the machine learning. And they are called the non-parametric approach, because possibly you know about regression analysis that has been covered in your course. I think I was going through the schedule that your coordinator has planned it. So there is a regression, then analysis or correlation analysis, whatever it is there. So they are basically non-parametric tests so far the learning is concerned. And in case of regression, you have to have certain data, and based on this data, you have to tell unknown value, and that is the regression model that you have to plan about it. So this is called the distribution free test, or it is also taking the hypothesis, because in this case also regression analysis, the result that will give you with certain error. Always in case of machine learning, or artificial intelligence, the 100% correct is not possible. There is a possibility of error, and our objective is to minimize the error so that we can improve the accuracy of the model. That is our objective. Anyway, so the one approach is called the non-parametric test. One example that I mentioned about regression analysis or correlation analysis, autocorrelation analysis, so many things are there. And in contrast to there is another is called the parametric test. So parametric test is basically based on the distribution. That is why if the earlier was distribution free test, then it's called the distribution based test. And as we have to have certain hypothesis, basically we have to tell something with certain confidence. That is why it is called the hypothesis. So this is the one approach is actually. Now usually the parametric test is applicable when population size is very large. On the other hand, non-parametric test is applicable when the entire population is at your disposal, and then you can build a model, learning model rather. Okay, and using this model, you can solve your unknown problem. And in case of parametric test, we usually interested about the mean variance of the population. So here also we assume that the population follows normal distribution, because as I already said that, okay, we have to follow Z distribution or T distribution, chi-square distribution. They are basically assuming that population follow normal distribution. And actually, in most of the situation, I am repeating again and again that, okay, most of the real life situation data, they basically are normally distributed. Now, so far the different sampling distribution is concerned, there are different parametric tests are involved. These are called Z test, T test, chi-square test, and F test. So here we will discuss about three tests, Z test, T test, and chi-square test. F test is related to analysis of variance whenever two or more population, and then we have to conclude from there, actually taking the sample from two populations, whatever it is there. So these are total different other application areas. Now, as I said you, Z test means here we assume that population means to be predicted, and knowing the population variance. If the population variance is known to you, and then you have to predict the population mean, then we can follow the Z test. That means having a sample, then you have to apply the Z test in that case. On the other hand, T test is applicable when the population variance is not known, and we have to predict the population mean. The same thing, earlier the population variance was known, but in this case population variance is not known, and we have to just infer about population mean. So in that case, we should apply T test for there. Now, chi-square test, actually, if the samples variance are known to you, that means sample satisfy a distribution which basically give the distribution of samples variance. If it is available to you, then we shall be able to apply the chi-square test to conclude about population mean. So these are the different three tests. Okay, we can understand that basic idea about is that we have to conclude about one population statistics, namely mean, whether population variance is available to you or not, or the distribution of the sample that is given or available to you, it is basically follow the variance or chi-square distribution. So these are the three distributions are basically important. Now let's consider about the statistical learning, the procedure as a whole. So first I will discuss about basic concept of statistical learning, and then the methods or the steps that is required to follow, to be followed, so that we can do statistical learning. Finally, we can discuss about errors. As I have already pointed out, and someone from your audience that asked a question about their errors and everything. So errors in hypothesis, it is also called the statistical learning. Hypothesis testing is also alternative naming of statistical learning, actually. So errors in statistical learning. And finally, we'll take a quick tour to case studies. One is the coffee cell and machine testing. Then we will be able to follow the basic concept here. Now, see, let us first learn about what is the mechanism of statistical learning. Now, this is a very simple picture. You can follow it, and this picture is basically, you can understand if I don't say anything about it, it is basically a courtroom scenario. So, in case of courtroom scenario, so there are two parties. One is the victim, and another is basically the investigator. And here victim basically maybe that he made crime or I don't know, whereas the investigator basically to prove that okay he made crime, and then for both the parties, that is for the criminal or accused basically and the investigator, there are two lawyers, we can say the advocates. They will advocate that okay it is okay he didn't make any guilty. On the other, investigator will try to prove that he made guilty. And whatever the justification from the two lawyers, it will be basically populated to the judge, and then judge will take a decision whether the argument made by the accused lawyer will be rejected or accepted, or vice versa. So this is basically the courtroom scenario. I gave this kind of pictures here because our statistical learning is basically related to this kind of scenario, very fitting way actually. Now we'll see exactly how this scenario is related to our actual scenario of statistical learning. Okay, now let's proceed. So here what is the concept of statistical learning? Again, I just want to repeat it. You have a population for any application scenario, for any business scenario that you have to deal with, for which you have to have a data analysis activity. And for population, right, there are statistics called the mu and sigma. You select at random one sample from the population, and from the sample you can calculate the sample mean and sample variance. So this is basically denoted this kind of figure here. Okay, this is very simple. So what I want to say is that you don't have any idea of the population mean actually, and you want to have the idea of this population. So mean and variance, if you are having, then from there whether you will be able to conclude the mean and variance of the entire population. For example, suppose you can take one survey about the GATE score of all students who appear in 2020 GATE exam, and then you want to conclude that the mean of the GATE score obtained by the student is 300 without taking the entire GATE score of all the students who appear the GATE exam. So it is idea about it, and then how statistically we can learn, and then we can predict that this is valid or not. So we just want to tell about okay this concept that mean is 300 is acceptable or not. So that is basically the concept of statistical learning come into the picture actually. Now, so here basically the idea is basically to test an hypothesis. As I said an example, we assume that mean is equals to 300. It is an hypothesis, and with this assumption we have to check whether this hypothesis to be accepted or rejected. Accepted means whatever the mean that we can assume it is correct. Reject means that mean that we have assumed it is not correct. And you see by that means actually we will be able to infer about population statistics. You can see how we are inferring or how we are concluding the population parameter by means of this test of hypothesis. So you have to perform test assuming certain mean and then either accept or reject. So this is basically the concept here. So the idea is that you take the sample, collect the sample, and sample is basically your data here. So this basically constitute to either in favor of your hypothesis or against the hypothesis. So here it basically will argue always that hypothesis is null, that means it is not valid, and here is alternative, no, it is valid. So this here. So either not valid or valid, and then the argument will be made based on the collection of data from the sample, and then that statistical inference will be made that okay, this hypothesis is acceptable or rejectable. So basic idea of the statistical learning is basically is to consider a hypothesis. A hypothesis means an assumption, and then we have to prove the hypothesis, or we have to we can say that we have to reject the hypothesis or we have to accept the hypothesis. So this is the basic concept about the statistical learning, as it is based on hypothesis and testing the hypothesis. So most of the cases also hypothesis testing is also used as an alternative of the statistical learning. Now here hypothesis, the keyword we are repeatedly using. what exactly the hypothesis concept it is there. Now you see there are certain concepts which can be proved mathematically, which has certain theorem, then we can say that it is a theorem or it is a proof. But sometimes, it is valid forever, but there is no mathematical proof, no formal mechanism to establish the concept. However, certain empirical way that we can prove it. So if it is like this, then that kind of concept, it is basically called hypothesis. Now, you probably know that from the study of physics or chemistry, there are many hypotheses used in our physical science. In mathematics also many hypotheses are known there. And in our research investigation, in many simulation, we usually consider hypothesis and try to validate the hypothesis, basically the idea. And one very popular hypothesis, it is called the Avogadro's hypothesis. And in this case of hypothesis, it basically relate the relation between two entities. Here, for example, the volume of a gas and the number of molecules of the gas. Okay, and it basically Avogadro hypothesis says that volume of a gas is directly proportional to the number of molecule of the gas. So this is the relation between the two. And it is again relation analysis. Okay, you can see that V is the one parameter, maybe that dependent parameter, N is the independent parameter. So the relation between the two. And you can take it as an hypothesis, and you can either prove or disprove it that this is valid or not valid. Okay, and if you can take a sample, a gas molecule, and count the number of molecules and measure the volume, and then you can verify and you can get it. That will give you the result that, okay, this hypothesis, that is Avogadro hypothesis, is acceptable. Otherwise, we can take that it is not rejected. Anyway, so Avogadro hypothesis this way established nowadays in physical science, and it became the what is called the standard one hypothesis known for and solving many problems. So this is the idea about the hypothesis testing. As an alternative OA, we can say that statistical learning or statistical hypothesis. So this is the concept, and there are many other examples that we will learn about, that how the statistical hypothesis is useful to solve many problems, and let's see how the different problem can be solved here. Now we are going to discuss about the procedure of statistical learning. The procedure, as we have an idea about, that it is basically mechanism between the two parties. That is why here the basic concept that it basically covers is that it considers two hypotheses. One hypothesis is called the null hypothesis, and another is called the alternate hypothesis. The two hypotheses are denoted at H0 and H1. H0 is called null hypothesis, and alternative hypothesis is denoted as H1. The two hypotheses are to be selected in such a way that they are exhaustive and exclusive. That means at the same time, both the same cannot be true. Either one is true, and if one is true, then other has to be false. So this concept is called the exclusive and exhaustive property. Now let us start with how we can define for a problem the null hypothesis and alternative hypothesis, and the detailed step about the statistical learning method. Now, in order to discuss about the two hypotheses, the null and alternative hypothesis, we can consider one simple example. And here is an example that I have mentioned here. It is a very simple example. You will be able to follow it easily. Our government of India, okay, the MHRD, usually conducts an examination year-wise to assess, right? Assess the standard of the different IITs that the government has set up. Okay, so 23 IITs now, and then we want to see it. Now, to do these things, they conduct one experiment. This experiment is basically GATE experiment, where all IIT students are asked to appear the exam. So usually we can take the total score of all IIT students who appear the GATE examination in every year, and then take the score of that one. Okay, so it is basically gives an idea about, because the GATE examination is to measure the engineering aptitude of the students, so graduate aptitude in test of engineering. So it is usually conducted on the 1,000 marks in every year. So here in our experiment, we can consider a sample of 300 students who appear gate examination in an year, and it is observed that their mean is 220. Okay, so these 300 students selected at random, okay, throughout the country wise from different IITs, right? And then we see that for this sample, the mean that we can observe is 220. Now, from this experiment, it is our task is to tell whether this 220 is the characteristics of the all students who appeared gate examination in 2018 or not. That is what actually we want to do it, right? So in this context, we can consider two hypotheses. First is a null hypothesis. Null hypothesis is that, let's see, mu equals to 220. That means we have to assuming that null hypothesis mu is 220. That means the population mean is 220. So if we can reject this null hypothesis, then we can say that, okay, so 220 is not the valid one proposition. Otherwise, it is that either 220 less or greater than alternative hypothesis that can be considered. So in this context, so two hypotheses, one hypothesis is null hypothesis. Null hypothesis always used as a equal sign, and then alternative hypothesis used as a either not equals, less than or greater than sign, whatever it is there. If the null hypothesis is rejected, then alternative hypothesis will be accepted, and vice versa. So our task is to basically whether we can reject the null hypothesis with sufficient data and then experiment, then we can say that this is basically the population mean. So this is the idea about the concept of null hypothesis, and it is the idea. Anyway, so there are again the two hypotheses that can be, we can plan for an experiment in a different way. If we consider null hypothesis in this form and then alternative hypothesis in this form, then we can say that these are the tests belongs to a particular category called the one-tail test. So hypothesis testing can be under two, right? One-tail test or two-tail test. So if the hypothesis considered in your testing procedure takes this form, then we can say one-tail test. On the other hand, if it is the null hypothesis like this, but alternate hypothesis is greater than or not equals to mean, right? Assume mean, actually this is the assume mean. Then such a test, right, is called the two-tail test. Now we will be able to understand what is the meaning of one-tail test and two-tail test and why the things it is like this one, because that is the procedure that okay, we are going to learn about it. We will be able to see that how the two tests, one-tail test and two tails matters actually. Anyway, so just assume that if your two hypotheses, one is equals to assume mean and it is basically greater than assume mean or less than assume mean, then it is one-tail test. Or on the other hand, if the mu equals to assume mean and then alternative hypothesis mu is not equals to assume mean, then it is called the two-tail test. It basically depends on the idea about this one. Now let's see what are the steps are there. The statistical learning procedure consists of 5 simple steps. So the first steps is basically for the test, that means for the decision that for which you want to do it, you first consider two hypotheses, H0 and H1. This is the first step actually. I mean two hypotheses that you have to consider, and then you have to test the two hypotheses whether H0 is acceptable or rejectable and vice versa. And in order to accept a hypothesis or reject whatever it is there are certain level of confidence to be considered. I will discuss in details about what it does mean. So it is basically related to the error that we want to add. If we want to minimize the error, our level of confidence should be small as possible. If we want to allow certain errors to be considered allowable, then we can have the acceptable level of confidence little bit higher value. So depending on alpha, we can decide about whether H0 will be how strongly we want to or how confidently we want to reject a hypothesis or accept a hypothesis. So that is why acceptable level of alpha is required there. Then we have to apply the test. We have already learned about your sample follow what type of whether Z test or T test or chi-square test. Depending on, we have to decide about the rejection region that this hypothesis will be rejectable or not. So that actually the test base, which test you want to apply. It basically depends on what sort of data that your sample follow or your sample basically obey. And based on this, we will be able to decide about rejection region. Then we have to ultimately collect the sample data and calculate if it is Z test, then Z value, if it is T test, then T value, if it is chi-square test, then chi-square value. And then we have to take, based on this data and then test statistics, we have to conclusion about whether we can accept or reject. Okay, and that is the idea about it. Now these are the 5 steps, but these 5 steps apparently, okay, maybe not understandable because you are possibly you are going through these steps first time. But once I clear it, then it will be very easy. And moreover, whenever we discuss about the case study, it will very easily understandable to there. So as again I repeat it, first step is to decide H0 and H1, the 2 alternative hypotheses, null hypothesis and alternate 2 hypotheses, null and alternate, and then level of confidence that basically a hypothesis will be either rejectable or acceptable. Then we have to apply the test. The test means either Z test or T test or chi-square test depending on the distribution. And then you have to decide about the rejection region, and then you reject a hypothesis or fail to reject hypothesis. That is accept hypothesis. So these are the 5 steps basically approach is there. Okay, we will decide about these 5 steps. Now here I just want to give a bit discussion about that. The all statistical learning procedure is basically involved with certain errors. Okay, so what are the errors are there? Actually, there are 2 types of error, right? So far your statistical learning is concerned. In other words, whether you can accept a hypothesis or reject a hypothesis regarding this one. So 2 types of errors, they are called type 1 error and type 2 errors. So type 1 error here is basically it is there. So type 1 error means you made the correct decision. It is in the sense that the null hypothesis is true and you have accepted the hypothesis, then it is correct. On the other hand, this is the type 1 error is basically when you reject the hypothesis, but actually reject the null hypothesis, but actually the null hypothesis is true. So this is called the type 1 error. Now there is type 2 error. Type 2 error says that you have accepted the null hypothesis, but actually the null hypothesis is not correct. And here you have rejected the null hypothesis and actually the null hypothesis is rejectable. So this is basically the confusion matrix it is called. And in this confusion matrix, we can identify the 2 errors that may occur. They are called the type 1 error and type 2 error. We are rejecting an hypothesis, but which is basically acceptable. And on the other hand, we are accepting a hypothesis, but actually which should be rejectable. So based on these 2 errors are there. Now these 2 errors basically can be calculated probabilistically because it is altogether everything is probabilistically. So here alpha basically says what is the probability that rejecting H0 but H0 is true, and beta is basically related to the type 2 error. What is the probability that we just accept H0 but H0 is not acceptable or rejectable or H0 is false. So these are the 2 errors are involved there. Now we'll see how these 2 errors can be calculated with a very simple idea that we can think about it. So I'm going to discuss about how these errors can be taken into account, and then accordingly we can carry out our statistical learning procedure. So let us consider 2 hypotheses, H0, and this is called the assumed mean, and assume the null hypothesis always use equal sign, and this is the another alternative hypothesis which is the assumed mean, and mu is not equal to this one. Okay, and this basically under the 2-tail test. Okay, now what is the idea about it? Idea means that for some A with certain value plus delta or minus delta, that means say suppose A is 300, we can take one value 350 or 250. So here plus minus delta we can say 50. That means this is the tolerance level. That means we can accept a hypothesis up to this tolerance, the plus minus 50 both sides. If it is there, then we can say that these are confidence level. And beyond this thing, that means if it is less than 250 or more than 350, then we confidently, based on this confidence, that we can reject it. So here is the tolerance. So mu equals to A, it does not mean that absolutely it is equals to A, but with little bit tolerance that we can allow it. And that tolerance is up to your confidence, up to the decision maker, which they can be flexible to give it that, okay, I can take the decision with this tolerance or this kind of what is called the approximation, we can say. So accuracy level is up to that only. So that is why plus minus delta. And here, basically the errors is coming is there. So error, even if you see, if the value of delta is bit high, then definitely we will be able to minimize the error. But in this case, the error will be both directions, either type 1 error or type 2 error. Okay, because if you want to reduce the type 1 error, it is possible that the type 2 error will increase and vice versa. So there is again trade-off. So if we can take the value very large or very small, then we have to think about both the errors are there. And altogether, both type of errors matters. So counting all two types of errors, basically ultimately, what is the error in your learning process? So that is what this is the concept. Now here, the concept of this error can be better described in case of statistical testing procedure. Now here, this graph you just take. This graph is basically distribution of sample, as we have already plotted is the normal distribution, standard normal distribution, whatever you can say. Let's say normal distribution. So normal distribution says that the sample mean is A. Okay, so this is basically the distribution of the sample. And these are the different samples mean, right, in this direction. Okay, fine. And now here, if we say that X bar, that is the sample mean, is basically greater than A plus delta, mean this direction. If the sample mean is greater than A plus delta, we can reject it because it is not the population mean line. Or on the other hand, if sample mean is less than A minus delta, then we can reject it. So what we can see is that if the sample mean is lying in between A minus delta and A plus delta, then we can accept the null hypothesis, otherwise we will reject the hypothesis. So that is why here alpha, the probability that we can make an error is basically if it makes within this region there. Now here again one more thing that you should notice, that here the total probability, that means is basically always 1 regarding whatever the decision you take, and because this is the area under the curve is exactly 1. So area covered by any distribution curve or probability distribution curve is always 1. And here is basically the percentage of area of this region is actually your confidence level. This is because if suppose 5% confidence level, if you can consider, then it is a 2.5% area of the probability is this side and 2.5% area in this side. Altogether, this shaded region is basically 5% of this one. So in case of this case, 95% you are confident about accepting a hypothesis, whereas 5% is basically rejecting. Okay, so on the other hand, if we take 1%, then means your acceptability will increase, whereas rejectability will decrease, and therefore leading to maybe more error or whatever it is there. So this way, the confidence level come into the picture. And confidence level is basically can be plotted in the distribution plot by means of this kind of drawing it is there. Anyway, now there are, okay, rejection region as I say. So all this white part is called the acceptance region. It is basically probability that a hypothesis will be accepted, and these are the area indicates that this is the probability that a hypothesis will be rejected. As I said already, there are two tail tests and one tail test. In case of two tail test, so there are basically the area or probability or the area of the probability curve is basically on the both sides. If it is a 5%, then 5/2% in this side and 5.2% in this side. On the other hand, if it is a one tail test, for example here, if it is less than, then it is only this side. If it is greater than, then only this side. So it is a one tail test. In case of one tail test, so they are the 5% confidence if we consider this area, and this is basically the area of the acceptance region. And this is also the, if in case of less than, it is there, and this is the area of the acceptance region. So they are basically two tail test. two-tail test means both sides, and one-tail test means either one side, either left tail or right tail, that we have discussed about it. Now, this understanding required in order to have the idea about different steps. So now we have understood about 5 steps. Out of 5 steps, H0 and H1, the two hypotheses are to be decided, and then the confidence level that we have to decide. Now, confidence level will be decided based on how much confidence you want to have. So far, you want to accept a null hypothesis or reject a null hypothesis, whatever it be. And that can be done by means of the sampling distribution that basically your sample follows. And based on the sample distribution, you will be able to identify the rejection region or the acceptance region. And based on the identification of rejection region, we can take a conclusion that assumed hypothesis will be acceptable or rejectable. So this is basically idea. Now let us proceed an example, and I just want to give the example with a case study. So it is basically case study related to a coffee sale. Consider there is a coffee shop. Coffee shop, earlier it was selling coffee, and they are selling coffee on the average around 500 cups per day. All of a sudden, there is a development in the area. For example, one new stations are coming nearby the coffee shop. As a result, many customers may go to that side and not maybe they are coming to the coffee, and therefore the coffee shop, coffee vendor can see that there is a deterioration of sale or not, whatever it is there. So exactly here is the statistical test that we want to perform, that okay, whether because of the new development of a new station nearby, whether the coffee shop will lose selling more coffee or less coffee, whatever it is there. Anyway, so you have to have the learning about it. That means whether statistics, what is the statistics about the coffee sale, whether it remains same or it is increasing or decreasing, whatever it is there. That is basically we want to conclude. Now to do these things, we can have a sample. As I said about central limit theorem, that minimum 30 sample is required. Anyway, in this example, I just want to take only 12 samples. It is okay, fine, for the understanding purpose, but actually you have to take at least 30 samples for the sale. So last 30 days you can take. So these are the basically for the last 12 days, what is the average number of coffee that the coffee vendor sold has been recorded. So these are the 12 days data. Okay. Now on the basis of this sample information, we are to conclude about whether the sale of the coffee has increased, remained same or decreased. Okay, so it is basically idea. Now this is very simple data, and if you analyze with your simple eyes, you will be able to say that okay, coffee sale remains same or whatever it is there. Provided that you can see earlier, before the development occurs, there is a average sale 500. Now from this data, if we see that sale remains same, then we can say like this one. But statistically, with the help of learning, we want to prove it, and that is why we have to follow it. So this is a good example to discuss the whole things that we have learned, we have discussed with a very simple example. And also in this case, you consider 5% level of confidence. That means 95% okay chance that you will be able to accept it, and 5% is that it is rejection. Okay, so the confidence is there. Okay. Now, so if you are much liberal, you can write 1% level of confidence. That means your acceptability will increase, whatever it is there. Now, so let us consider this is the one example. So the sample here in this case consists of 12 days average coffee sales, and then population mean is basically assume that 500 because earlier sale is 500, and we have to conclude it above. Now for this sample data, we have to specify H0 and H1. Now you can understand little bit what should be the H0. H0 is basically assumed mean. So in this case, assumed mean is basically H0 is equals to 500. Assume that the coffee sale has not changed. Means neither increase nor decrease. Rather, we can say it remains same. Now we have to establish that whether coffee sale has remained same or changed. If we can reject it, then we say that either coffee sale has increased or decreased. Now again, increase or decrease, we have to test it with another hypothesis testing or another statistical learning testing. So here H0 and H1 are to be decided. So the null hypothesis is basically assume that 500, and we assume alternative hypothesis that mu is more than 500. That means the coefficient has increased. So if we accept it, then we cannot accept this one because it has not increased. But if we reject it, then we can say that it is there. Then again, another test we can perform alternatively. Anyway, so let's proceed it. So this is the first step that we can think about deciding two hypotheses. In this case, we consider the mu equals to 500 and mu is less than greater than 500 is the assumed mean is 500. Now, for the given sample, here we can see about so for the sample we want to have the mean, but in the problem statement or in the data that we have collected, nowhere they said about the population variance. This means that the sample that we have, we don't have any idea about the population variance. But from the sample we have the sample mean as sample variance, because from this data we shall be able to calculate the mean and variance easily. Okay, so we have the idea about means and variance, that is the mean and variance of sample, but we don't have any idea about population variance. So in that case we should apply t-test, because this problem is solvable using t-test, because t-test gives you the sampling distribution when the population variance is not known to you. So it is the case here. So according to t-test, the formula that we already have mentioned about our t-test formula is that x bar, that is the sample mean, minus it is the assumed mean, by the sample variance divided by sample size. So in this particular example, the sample mean can be calculated at 548, and then this is the sample mean, and n is the total number of data is 12, and the sample variance that can be calculated is basically 46.68. Okay, so this is the sample variance. Then the t-value that can be calculated for this sample that can be calculated as 3.558. So this is the t-value. Now you can recall about these are random variable value t, and that means this is basically tell about that how the sample mean is basically varying with a certain probability of this one. Now with this having the t-value, that we have to see about this t-value lies whether in the rejection region or in the acceptable region. If it is in the rejection region, then we can reject it, otherwise we can accept it. Now in order to decide whether t is in rejection region or acceptance region, you can recall about what I wanted to say about rejection region and acceptance region. This graph actually it is there. So your t-value it is there. Then if t-value lies in the rejection region, then we can say that it is rejectable. So it is the two-tail test, one-tail test, so I can see if the t-value lies here in any region, so this is basically t-value, right? And then if t-value lies in this region, then we should reject it. If the t-value lies in this region, then we can accept it. That means if t-values that for the given sample, we have to check if greater than, this is the critical value. This critical value is decided by the confidence level, alpha. Now, what is this critical value? That can be obtained from the statistical table actually. A table is there. This table basically plot all the values of t's with certain degrees of freedom and the level of confidence. So there is a table, basically table gives the degrees of freedom versus level of confidence, and then for a particular level of confidence and for a particular degrees of freedom, it basically gives the t values that basically tell about the critical region. Now in this case, let us see what is the alpha and what is the degrees of freedom. Now as I said already, alpha it is one-tail test, so alpha is basically 0.5 in this example, and degrees of freedom here n number of data. As you know, a list of n samples, the degrees of freedom is always n minus 1, so it is 11. So what we have to do is that we have to consult the statistical table for alpha equals to 5% and degrees of 11. So there is a table here. So this table for different values of alpha and for different degrees of freedom, for degrees of freedom 11 and for alpha 5%, it will give one t values. And now let's see what is the t value that we can have. From the t distribution table, we can see that this t value is 1.796. So 1.796 means that if we see this curve here, so it is basically 1.796. This is the t-value that we can obtain from our t-test. And now our t-value for the given sample, it shows that 3.58. This means that this basically in the rejection region. This means that the hypothesis that we have assumed it here is mu equals to 500 cups per day is rejected. That means the copy cell has increased. So this is basically because it basically suggests alternate hypothesis that is assumed there. So here the object value of T, which is in the rejection area, thus H0 is rejected. So what we can conclude is that the sample data indicates that copy cells have increased. So this is the idea about the hypothesis testing that we can think about with a simple example of the copy cell. Now let us consider one more example to consider the things better. In this example, we will consider about we have to have the confidence about accuracy of a bottling machine. It is, so a medicine production company packages medicine in a small tube. Let us see the capacity of the tube is 8 millimeter. So it will be labeled as the quantity 8 milliliter. But whenever the medicine packaging machine use it, in some machine it can be little bit more than 8 milliliter or little bit can be less than, because the machine accuracy cannot be exactly 8 milliliter. Now in order to maintain the control in the amount in the medicine tubes, that is the machine is used. So it is basically to decide whether the bottling and the medicine packaging machine is working perfectly or not. In order to do these things, what actually the test we can do is that a 16 tube at random in the production line, from the production line we can take it about. And so that is why 16 tube is taken from the production line at random and with certain interval of time, not that same time, right? So this basically gives a random sample that needs to be considered in order to have our statistical learning. And from the 16 tubes that we have considered, the mean amount of medicine in these 16 tubes will have to be tested using hypothesis that it is 8.0 or more 8.0 or less 8.0, whatever it is there. And also from the medicine bottling, we assume that the variance that can be allowed with certain value. Let the variance is, we can consider variance is 0.02 or whatever it is there. Now let us consider here first step that, in this example, the two hypotheses. So null hypothesis and alternate hypothesis. So null hypothesis, we are assuming that mu equals to 8. This means that assume mean is basically 8. That means machine is working perfectly. The alternative hypothesis that mu is not equals to 8. That means machine is not working perfectly. Now here 8 means not exactly 8, but with certain tolerance that will be taken by this confidence level. So let us consider the confidence level again in this example is 5%. So usually in statistical learning, the confidence level taken within 1 to 5%, this is the golden rule that we follow. Okay, if you are very much liberal or if you are very much conservative, then you take either 1% or you take either 5% depending on. Okay, so this is basically standard procedure and it is adapted procedure that we can follow. Now anyway, in this case, we have two hypotheses that we have considered, null and alternative. And in contrast to the previous example, as you can see, it is basically become the two-tailed test because the alternative hypothesis assumed not equals to 8. That is why it is under the two-tailed case. Anyway, for the two-tailed test, the rejection region that can be obtained from the Z. Here Z basically we are following because somehow you have given population variance. So population variance is known. If the population variance is known, then we should apply Z test. In contrast to the previous example, where the population variance is not told to you, and that is why we assume t-test. So t-test versus z-test depending on population variance is known, given to you or not known. So here in this case, it is known, so it is there. Now in this case, what we can see is that alpha for confidence level 5%, the Z value that can be obtained is 1.96. That is from the standard normal distribution table that we can have with the 5% confidence level. So normal distribution table basically gives you the what is the confidence level and what is the values of Z for the critical region, that from which actually rejection region will start, whatever it is there for a given degree of freedom. It is the same as t-test look like. Now for the given sample, from the sample data, the size of the sample is 16. The sample mean that can be obtained because we have collected the 16 tubes, and from these 16 tubes we can calculate 7.89. Assume that it is calculated as the mean, sample mean is 7.89, and population mean is given as 0.2. As I said earlier, assume that population mean is given. That means 0.2 variance. That means dispersion among the mean is allowed actually. That is why it is basically that 0.2. Now with the sample, the test statistic Z can be calculated. This is basically observed mean from the sample. This is the assumed mean, and this is basically sample variance, size of the sample, and it gives basically 2.20. So the Z value is 2.20. On the other hand, the critical region is 1.96. So what exactly we see that Z is basically critical region is 1.96, and for the given sample we calculate the Z value is 2.20. Therefore, it is basically within the rejection region. This means that here H0 is rejectable. So we reject the hypothesis, means that the bottling machine is not working as it is required to be work actually, or as expected. So machine should be adjusted because it basically reject the hypothesis. Or you can say that mu is not equals to 8. That is basically proved it is there according to this hypothesis. Now we can test the same experiment but with a different value of alpha. Now let us see what is the conclusion. That is what I wanted to tell you. If alpha value, that means the level of confidence varies, but for the same settings, then what will happen? So now let us consider instead of 5%, the alpha confidence is assumed as 1%. So it is alpha is 0.01. Now again, as it is Z is 2.576, because of this Z equals to 0.1, and same thing is there 2.20. Now here the critical region, earlier the critical region is 1.576, but here is basically 2. Here earlier in the earlier experiment, the critical region is 1.96. But as we change the alpha value to 0.01, the critical region becomes 2.576. So this means that the earlier, which one is basically here, the earlier value is 2.20, right? Here also 2.20 for the same sample, but this 2.20 is basically here. So in this case, our observed value is 2.576. That means it is here. Our critical region shift, it is here, 2.576. And for the sample data, it is 2.20. This means that the 2.20, the sample that we have calculated for this level of confidence, it is in the white region. That means it's the acceptable region, because rejection region starts from here onwards. And therefore, we reject it. We accept it. So the same hypothesis, which basically have rejected for alpha is 5%, is basically rejectable at 1%. This means that the level of confidence matters, or what I can say that level of confidence is very important so far your accuracy is concerned. So if we have less accurate prediction, then you can take the level of confidence little bit less, and if you have to take the more accurate result, then you can take the level of confidence little bit higher value. So depends on this one. So these are basically the concept of statistical learning that I wanted to convey it in this class. What I want to say is that here basically two hypotheses you have to test. You have to assume these two hypotheses, perform experiment, and then either accept or reject. That is basically the procedure. And in this procedure, we have to take the confidence of sample, and you have to have the sample following certain distribution, assuming that it follows this one, and then you can do the test according to that sample distribution that it follows. But at the ground level, what you can say that you can have a very small amount of size of the sample, and then knowing the property of the sampling distribution, you will be able to do it, and then accordingly you can take the decision making. But whatever the decision making that you can take, it is basically subject to the error. And the error, basically, there are two, type 1 and a type 2 error. Altogether, the total error will be counted towards the performance estimation or accuracy measurement. So this is basically the idea about statistical learning. The measurement of accuracy, performance, and all these things are same as the machine learning approach, like precision, recall, F1 score, whatever it is. Basically, they are basically based on the confusion matrix. In this experiment also, you can do lot of tests for the same sample, and accordingly we can do certain confusion matrix and then count the type 1 error and type 2 error, and finally you can judge about that. For this sample, this is the data, this is the accuracy that we can obtain, and after this test. So this is the idea about the sample test. And the discussion that I made just now, okay, most of the discussion you can find in the book Probability and Statistics for Engineers and Scientists. It is available as an ebook freely. Many of you already know, I think those are the teachers for maths and everything. They are, I'm sure that they know this book very well. It's a very good book on the field. And there are few more books also for statistical learning. One good book is called Essential Statistical Learning. It is called the ESL, the book from the Timberseny from Addison Wesley. That is also very excellent book for the statistical learning purpose. Anyway, I have a few minutes, I think, if you allow, maybe 5 minutes max, because I have given time till 6:15. Anyway, so I can take 5 minutes or so that I can take few questions from you and try to clear your doubts if you have. So please ask question.
Yes, sir. Actually, all experiments are depending on the level of confidence. So
Yes.
how we can get the level of confidence? Which parameters will give this one?
Correct. Actually, there is certain limiting values of alpha, because what I want to say, there is a lot of mathematics are possible. There are certain limiting values of alpha, means if you decide an alpha value in such a way that whatever be the sample you collect, always a test hypothesis will be rejected, or alternatively will be accepted. Now, so there is a detailed procedure I have not included in this discussion because of the shortage of time, that you can decide about it. Now, if you know this limiting values of alpha, then you will be able to decide your required values of alpha. This is why in the first step is very critical step. First step is basically, you see, there are actually hypotheses that you have to decide. Now, you can assume the mean according to your own wish, right? And then accordingly the alpha also according to your own wish. But you have to be little bit meticulous about deciding what should the assume mean. Actually, you have to prove a hypothesis. Hypothesis that my assumed mean is this, and I want to either prove it or not prove it. And then limiting value of alpha, say suppose limiting value of alpha is, okay, say suppose 0.1%. This means that if you have the 0.1% is the confidence level, then whatever be the data that you can, always will be rejected, or whatever it is there. Then you have to decide that, okay, I should not take the values of alpha 1%, 0.1%, rather I should take little bit, because I cannot take the audacity to reject all the hypotheses. That should not be. So I can take a value depending on that, okay, limiting value, and we can take safely this value. Now, okay, I can take safely in the sense that how conservative you are or how liberal you are to accept a thesis. So it is basically prerogative of the decision maker, prerogative of the engineer who basically do the testing. Yeah, I agree that it depends on that value, that is obviously, but it is totally depends on expertise of the data analytics engineer who basically do the test.
Okay, sir. For every different experiment, it will be differ based on the expert.
Expert, correct. That is because the expert is actually, yes.
Okay, sir. Thank you, sir.
Yes, thank you. Welcome.
Hello, sir.
Yes.
Is it not false either in the null hypothesis or it will be alternate? Then how could we follow?
No, we have decided the hypothesis in such a way that they are exhaustive. That is why I told you, you have already decided the hypothesis. You cannot select some hypothesis which is not satisfying mutually exclusive and exhaustive property. For an example, I can tell you, Say suppose H0 is mu equals to A. You understand? And H1 is mu is not equals to B. But this is not a properly chosen hypothesis. And in that case, you can think is that it is neither in this region or not in this region or both in this region. It's not that. That it is not that exclusive property or exhaustive property. You understand? So the hypothesis that you have to choose in such a way, it satisfies exhaustive property as well as exclusive property. If you do it, then it should be either acceptable or rejectable, not both. That is why your question will, situation will never come. It is not possible.
Okay, sir. Especially why I am asking this in biological samples. So the probability of the sample sizes and sample variation is very high. And in such case, if they are not in a line of fall of either the null or in the alternate, how could we solve that?
No, I could not. Okay, make it. What you have? Please repeat the question. You say that. Yeah, repeat it, please again.
The biological samples, generally variation as well as the size will be more.
Yes.
In such case, if it is not in a fall of a line of null or in an alternative hypothesis, how could we solve that kind of variance in such a sized population?
Yeah, that is okay. So here basically that depends on, okay, so in that case, we have to have certain other testing procedure, okay? Because statistical learning is the one step towards your data analytics. There may be some other testing can be carried out, which basically can give you more confidence about the case that you have told about it, okay? So there are actually, this is one part only. There are more, maybe say, the likelihood estimation and everything that can be carried out later on, and then we can have the conclusion about it. So it is one way of doing the statistical learning, is one step we can say, but it is not the only step. There are few more things that you have to take, and then you can conclude it.
Okay, sir. It's a general case, I have understood what the concept you explained. But in terms of biological samples,
yes,
so yeah, there will be a size population, size variation, and also the variance is huge.
Yes.
In that case, the probability of defining such the parameters, how can it will not fall either in null, not be satisfied, not in the alternate is not satisfied. In such case, how could we follow that one?
Yes. So actually, this is the procedure that I have discussed about. It is basically single population and also limited size of population, or population follows normal distribution. Now again, there are many other type of population, or we have to conclude from the different groups, right? Different populations, rather different category of population, but they can be categorized. You understand? But within the same population, we can have the subdivision of the population. But in that case, actually, this test cannot be applied. Z test or T test or chi-square cannot be applicable. In that case, you have to apply the analysis of variance. So there is another discussion. Analysis of variation is a different topic. I told you, so statistical learning is only the thing that I have discussed today. There are many more things actually. So analysis of variance or maximum.
I'm told that will be mainly of normal way of distribution.
Yes, exactly. Correct. This is a very simple one case situation that I have discussed here. Correct, you are right.
But in biology, it will not be like that.
Yes.
So it will be all different game in that.
Correct. Sure.
So at that time, we have to apply the ANOVA. Thank you, sir. Thank you very much.
Okay, thank you very much. So if you have any questions,
sir, one question in the chat box. Sir.
Yeah, right. Let me see the chat box because I'm back in the. Okay, I'm just okay.
I'll read, sir. Is significance level constant or changeable in hypothesis?
Chat box. There are many questions coming. Okay, there are many questions in the chat box. Okay, fine. Just a minute.
The chat box, all appreciation, sir. One question is there. Is significance level constant or changeable in hypothesis testing?
Is significant level okay, fine. Now that is okay, good question.
It is asked by Abhishek Roy.
Yes. Actually, see, I gave some idea about it, that what should be the significance level, that you have to think about it. Now, so okay, fine. Now suppose you have to take a decision which is very critical. Now, if it is a critical, then significance level should be as high as you can take it, basically, because it is critical decision, and then you may not tolerate much error about it. You have to be a little bit too much accurate about it. Now, again, the idea of that, okay, if you take the significance level in a little bit conservative manner, then the idea is that either type 1 error or type 2 error will be influenced. So there is a trade-off. So if we take a very high value of significance level, then it is possibility that it will reduce the type 2 error, but type 1 error will be increased. So now there is a trade-off. Trade-off means it's very difficult. So that is why we have to do certain testing or trial and error method. Then okay, then I can see that okay, with this significance level, what is the type 1 error, what is the type 2 error. If we change it, then what is the type 1 error, what type 2 error. Then you can plot one curve like it is a characteristic curve, and based on which we can take one alpha value, is basically that I can take that, okay, both the error is basically acceptable level. So this is the idea. I can take that it should not be constant. It can be based on a lot of experiment, and then after the lot of experiment, then right value of alpha for a particular data or in a particular application scenario will be considered. So the summary is that it is not constant. You have to with a lot of experiment, and basically we have to decide it empirically. So here the question is that hypothesis test is only suitable for binary classification. Actually, it is not that classification problem. Actually, okay, in the line of machine learning, whatever it is, that you are not predicting actually, but we are concluding rather. Okay, so there is a difference between a prediction and conclusion in that sense. So it is not that binary. Why I should say that it is not binary? Because you can take the different assumed mean, for example, where you want to conclude or infer the statistics, population statistics, then your level will be different. So it is not in that sense a binary classification. It is not exactly classification problem in that sense. It is basically problem regarding that either testing. We can say that we have to infer. It is about the inference. It is about the inference of certain population parameters. That is why it is not that classification problem. So it is not exactly binary. Then yes. So okay, fine. So this is the question that I can. Okay, good. Yeah. Yeah, time is too short.